subscribe, click on the bell, like, comment.
Section 10 of Seeking a Human Spaceflight Program Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McAfee, Merritt Island. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 4.0 Current Human Spaceflight Programs, Part 3. 4.3 The Constellation Program. In addition to the Shuttle and the ISS, the scope of NASA activities the committee was directed to examine includes all of the activities within the Exploration Systems Mission Directorate, ESMD. These include the Constellation Program, the name given by NASA to the flight development program for the next phase of human space exploration. As the committee assessed the current status and possible future of the Constellation Program, it reviewed the technical, budgetary, and schedule challenges that the program faces today. In developing integrated options for the nation's human spaceflight program, the committee established as the baseline what it considers to be an implementable version of the Constellation Program. This baseline case is outlined in more detail in Chapter 6. The 2004 Vision for Space Exploration established new and ambitious goals for the nation's human spaceflight program. The Constellation Program is NASA's response to that vision. The Exploration Systems Architecture Study, ESAS, defined the broad architecture for the program in 2005. The principal program elements include the Ares-1 launch vehicle, capable of launching astronauts to low Earth orbit, the Ares-5 heavy-lift cargo launch vehicle to send astronauts and equipment towards the Moon or other destinations beyond low Earth orbit, the Orion capsule to carry astronauts to low Earth orbit and beyond, the Altair lunar lander for descent to the surface of the Moon and ascent back to lunar orbit for the crew, and surface systems that astronauts will need to explore the lunar surface. Development of the first two of the elements needed, the Ares-1 and Orion, is well underway. While development of the Ares-5 has not been initiated, certain components of the Ares-1 can be expected to be common with the Ares-5. A detailed review by the committee of the two launch vehicles, the Ares-1 and Ares-5, will be presented in Chapter 5. The Altair lander and the lunar surface systems are still in very early phases of design and were discussed in part of the Moon First strategy in Chapter 3. 4.3.1 Orion. The remaining principal element, Orion, consists of a spacecraft generally in the shape of the Apollo capsule, a service module, and a launch abort system. Orion is designed to operate in space for up to 6 months and carry 6 astronauts, but is currently being configured for ISS support as a 4-person vehicle. An upgraded Block 2 version is anticipated for travel to the Moon and beyond. Orion performance is constrained by re-entry and landing considerations and is also subject to limitations imposed by Ares-1. It has undergone multiple redesign cycles in response to changing requirements. The committee examined the design and operations of Orion in some detail. Many concepts are possible for crew exploration vehicles, and NASA clearly needs a new spacecraft for travel beyond low Earth orbit. Evidence reviewed by the committee indicates that the current Orion design will be acceptable for a wide variety of tasks in the human exploration of space. The committee's greatest concern regarding Orion is its recurring cost. The capsule is 5 meters in diameter, considerably larger and more massive than previous capsules, for example, the Apollo capsule, and there is some indication that a smaller and lighter 4-person Orion could reduce operations costs. For example, such a configuration might allow landing on land rather than in the ocean, and it might enable simplifications in the currently large and complex launch abort system. In addition, this would also increase launch margin, which could reduce the cost and schedule risk to the Constellation program. However, a redesign of this magnitude would likely result in well over a year of additional development time and an increase of perhaps $1 billion in cost. In any case, in order to provide for a sustainable program, every effort should be made to reduce the recurring costs of Orion. Safety is, of course, a primary concern in any human-rated system, and Orion and its companion Ares 1 launcher are designed in accordance with NASA's latest human rating requirements. The design includes an abort capability throughout ascent, as well as requirements to make loss of crew a factor of 10 less likely than at any previous time in human spaceflight. The ability of Ares 1 to meet these requirements will not be known until it is an established flight record, but it is clearly being designed to a high standard of safety and reliability. A more detailed discussion of human rating is contained in section 5.3.4. As part of an independent review, an assessment of the Orion crew vehicle stand-alone development plan was conducted. The assessment focused on critical path elements. It was observed that the Orion development schedule is back-end loaded, such that designing test articles, conducting tests, and producing flight hardware run in parallel, thus creating an extremely high schedule risk. For example, the program of record shows only 3 months between completion of system qualifications, June 2014, and the planned Orion 1 launch date, September 2014. A large number of technical risks also add to schedule uncertainty. When compared to historical programs, the most likely delay to the Orion availability approaches 18 months. Additional critical paths exist through ground and flight test. 4.3.2 Constellation Development. Since Constellation's inception, the program has faced a mismatch between funding and program content. Even when the program was first announced, its timely execution depended on funds becoming available from the retirement of the Space Shuttle in 2010 and the decommissioning of the ISS in early 2016. Since those early days, the program's long-term budget outlook has been steadily reduced below the level expected by NASA. As shown, the Exploration Systems Architecture Study of 2005 assumed the availability of a steady-state human spaceflight budget for exploration of about $10 billion per year. In the subsequent FY 2009 and FY 2010 budgets, the long-term projections for funding have decreased. The FY 2010 President's Budget submittal suggests a steady-state funding of about $7 billion per year. The shorter-term budget situation has had mixed impact on Constellation. The formal first post-ESAS budget was the FY 2007 budget, in which the funds available to Ares 1 and Orion were significantly lower than those anticipated during the time of ESAS. Subsequently, in the FY 2008 FY 2010 budgets, the funds anticipated in the out years in the FY 2007 budget were made available to Ares 1 and Orion. In part, this has been achieved by scope changes in other NASA programs. The budget outlook for the Constellation program would be even bleaker under some alternate human spaceflight plans. Without additional funding, if the shuttle manifest exists into 2011 and/or the life of the ISS is extended, there will be even less funding available for Ares 1 and Orion. Further, as the shuttle and ISS programs are terminated, a significant percentage of NASA's fixed costs will transition to Constellation. The committee has found that not all of these costs have been accounted for in the Constellation budget plan. Most major vehicle development programs face technical challenges as a normal part of the development process, and Constellation is no exception. For example, as the Ares 1 design has matured, the rocket has grown in weight and various technical issues have emerged. Among these is the high level of vibrations induced by thrust oscillation in the first stage motor. While significant, these can be considered to be engineering problems, and the committee expects that they will be solved, just as the developers of Apollo successfully faced challenges such as a capsule fire and an unknown and potentially hazardous landing environment. But finding the solutions to Constellation's technical problems will likely have further impact on the program's cost and schedule. Differences between the original Constellation program planning budget and the actual implementation budget, coupled with technical problems that have been encountered on the Ares 1 and Orion programs, have produced the most significant overall impacts to the execution of the Constellation program. This has resulted, for example, in slipping work on the Ares 5 and lunar systems well into the future and setting Orion's near-term occupancy at 4 astronauts. The original 2005 schedule showed Ares 1 and Orion available to support the ISS in 2012, only 2 years after scheduled shuttle retirement. The current schedule maintained by the Constellation program now shows that date as 2015, but with a relatively low schedule confidence factor and little schedule slack on the critical path. The committee commissioned the Aerospace Corporation to perform an independent assessment of the technical, budgetary, and schedule risk on the Constellation program. The study methodology employed for the assessment of cost and schedule is substantially the same as described for the integrated options of Chapter 6. All resulting cost and schedule impacts prepared for the committee are formulated at the 65% confidence level, consistent with the direction NASA has given the Constellation program. The results of the analysis indicate to the committee that, under the FY 2010 budget profile, there is likely an additional delay of at least 2 years, with first launch in 2017, and perhaps as much as 4 years of delay, with first launch in 2019. This suggests that Ares 1 and Orion will not reach ISS before the station's currently planned termination. Assuming a shuttle retirement sometime in FY 2011, the length of the gap in which the U.S. will have no independent capability to transport astronauts into orbit will be about 7 years. The Constellation program has identified measures such as ongoing content reduction, deployment of stimulus funds to address high-risk schedule areas, and program management actions to mitigate major risks that suggest that the first launch of Ares 1 and Orion could occur in 2017 if those measures are successful. The Ares 5, still in conceptual design, promises to be an extremely capable rocket, able to lift 160 metric tons of cargo into low Earth orbit. But its design, too, has experienced growth and program delays due to the impact of the development of other elements of Constellation. Under the FY 2010 funding profile, the committee estimates that Ares 5 will not be available until the late 2020s. Under the FY 2010 budget, the lunar landing and surface systems will also be delayed by over a decade, indicating that human lunar return could not occur until well into the 2030s. 4.3.3 Importance of Technology Development. As currently structured, the only broad-based space technology program of NASA is contained within the Exploration Systems Mission Directorate and is closely tied to the near and midterm needs of Constellation. Two recent reports of the National Research Council have examined and made recommendations to NASA on the structure of its future space technology program. The need for technology development is apparent, and the pursuit of a well-crafted technology program would be very beneficial to the longer-term human spaceflight program. Failure to adequately fund such efforts in the past has reduced the options available today. Further, substantial cost and schedule savings can be achieved by having the needed technologies in place prior to initiating engineering development activities. Almost invariably, to conduct such efforts in parallel is extremely costly. Based on these considerations, the committee finds that a robust technology development program funded in support of future human spaceflight activities would not only introduce new opportunities for mission architecture, but also enable reduction in the cost of human spaceflight. This will be discussed in Chapter 7. Findings on Orion and Ares 1. Orion. The Orion is intended to be a capable crew exploration vehicle, and the current Orion design will be acceptable for a wide variety of tasks in the human exploration of space. The current development is under considerable stress associated with schedule and weight margins. The primary long-term concern of the committee is the recurring cost of the system. Ares 1. Ares 1 is intended to be a high-reliability launcher. When combined with the Orion and its launch escape system, it is expected to serve as a crew transporter with very high ascent safety. The Ares 1 is currently dealing with technical problems of a character not remarkable in the design of a complex system, problems that should be resolvable with commensurate cost and schedule impacts. Its ultimate utility is diminished by schedule delays which cause a mismatch with the programs it is intended to serve. Other findings on the Constellation program launch vehicles are in Chapter 5. End of Section 10. Recording by Patrick McAfee, Merritt Island.
Section 11 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 5.0 Launch to Low Earth Orbit and Beyond, Part 1. Launch to low Earth orbit is the most energy-intensive and dynamic step in human space exploration. No other single propulsive maneuver, including descent to and ascent from the surfaces of the Moon or Mars, demands higher thrust or more energy, or has the high aerodynamic pressure forces than a launch from Earth. Launch is a critical area for spaceflight, and 2 of the 5 key questions that guide the future plans for U.S. human spaceflight focus on launch to low Earth orbit, the delivery of heavy masses to low Earth orbit and beyond, and the delivery of crew to low Earth orbit. 5.1 Evaluation Methodology for Launch Vehicles. Launch vehicles and associated ground infrastructure are key elements of the architectures that support human spaceflight missions. Launch vehicles are generally designed anew or adapted from existing vehicles to support a specified mission or range of missions. The mission definition drives the size, performance, production rates, reliability, and safety requirements. This is particularly true for clean sheet, that is, new designs. For the adaptation of existing launch vehicles to new missions, greater compromise between the launch vehicle and the mission is often needed in order to execute the adaptation and thus realize the benefits sought. Primary among these benefits is proven safety, cost, reliability, and performance. The Aerospace Corporation performed for the committee an evaluation of potential launch vehicles. The metrics used in evaluating the various launch vehicle candidates, as shown in the upper left-hand corner of Figure 5.1-1, contain the usual cost, performance, and schedule parameters, but also include items such as safety, operability, maturity, human rating, workforce implications, impacts on the U.S. industrial base, the development of commercial space, the consequences to national security space, and the impact on exploration and science missions. Some metrics could be evaluated quantitatively, such as cost and schedule, while others required qualitative assessment, such as the impact on as yet undefined national security space missions. At a summary level, the assessment process centered around 2 evaluations. The first was to assess and modify, where appropriate, the claim for a system as submitted by the provider of that system. The second step was to represent the uncertainty associated with the assessment of each metric for each launch system. This process made it possible to capture cases where claims might be judged to be less than their stated values, but with a fair degree of certainty, as well as cases where a claim was judged well within historical bounds, but significant uncertainty remained about the estimate. It also permitted at least a first-order comparison of existing vehicles with proposed vehicles, including defining the uncertainty in that comparison. A sample summary of these evaluations is shown in the upper right-hand corner of Figure 5.1-1. In analyzing individual launch vehicles, the study approach examined approximately 70 lower-level metrics that contributed to the 13 top-level metrics. A summary was created for all relevant launch systems for each mission category as to their ranking relative to the other launch systems capable of supporting that particular mission. 5.2 Heavy Lift to Low Earth Orbit and Beyond. The insertion of heavy payloads from Earth orbit towards their destination is essential for exploration beyond low Earth orbit, and such systems significantly benefit from heavy lift to low Earth orbit. The plan of the Constellation program for the exploration of the Moon envisions launching about 600 metric tons per year to low Earth orbit, while exploration along the flexible path may require somewhat less launch mass each year. NASA scenarios for the exploration of Mars will have comparable annual requirements. In the 3 years of lunar surface exploration during Apollo, which had a less capable lunar surface infrastructure than is currently planned, NASA launched over 250 metric tons per year. As a point of comparison, the International Space Station, assembled over the last decade by the Shuttle, has a mass of about 350 metric tons. Thus, in the era of exploration beyond low Earth orbit, we will launch to low Earth orbit a mass comparable to that of the entire International Space Station every year. The key decision for heavy lift to low Earth orbit is on what should the next heavy lift launch vehicle be based. The committee examined 5 candidates for heavy lift, with their estimated launch mass to low Earth orbit shown in the rightmost 5 bars of Figure 5.2-1. In the end, to simplify the considerations, the committee treated the 5 launchers in the 4 classes summarized in Figure 5.2-2, the currently planned Ares 1 and Ares 5 architecture, the Ares 5 Lite, used in a dual mode for lunar missions, a shuttle-derived vehicle, and a Super Heavy launcher derived from Evolved Expendable Launch Vehicle (EELV) heritage. The shuttle-derived class was used to represent both inline and side-mount vehicles, each of which will be discussed in detail below. 5.2.1 The Need for Heavy Lift. First, the committee examined the question, do we need a heavy lift capability? While it is obvious that the ability to inject massive spacecraft away from low Earth orbit is vital for exploration, there is some question as to the smallest practical size of the launcher that will be used to carry cargo to low Earth orbit. The committee reviewed the issue of whether exploration beyond low Earth orbit will require a super heavy lift launch vehicle that is larger than the current heavy EELVs, whose mass to low Earth orbit is in the 20 to 25 metric ton range, and concluded that it will. However, the rationale for this decision is subtler than usually thought and hinges on 3 factors: the size and mass capability of the launcher and of the entire U.S. launch capacity, in-space refueling capability, and the launch reliability expected for a given mission. No one knows for certain the mass or dimensions of the largest piece of hardware that will be required for future exploration missions. It will likely be larger than 25 metric tons in mass, and may be larger than the approximately 5-meter diameter fairing of the largest current launchers. The largest single element in the current NASA plans that will be launched to low Earth orbit is the Earth Departure Stage, EDS. Not counting its approximately 60 metric tons of payload, the EDS arrives in low Earth orbit on a standard lunar mission with a mass of about 119 metric tons, of which about 94 metric tons is fuel and only 25 metric tons is dry mass. In the absence of in-space refueling, the U.S. human spaceflight program will require a heavy lift launcher of significantly greater than 25 metric tons capability to launch the EDS and its fuel. However, the picture changes significantly if in-space refueling is used. All of the heavy lift vehicles listed in Figure 5.2-2 use an EDS to lift the specified payload mass to low Earth orbit. In the conventional scheme, the EDS burns some of its fuel on the way to orbit, and it arrives in low Earth orbit partially full. The remainder of its fuel is expended in injecting the payload towards its destination beyond low Earth orbit. The alternative is to refuel the EDS in low Earth orbit from either a dedicated tanker or a fuel depot. This allows more mass to be injected from the Earth with a given EDS. Studies commissioned by the committee found that in-space refueling could increase by at least 2 to 3 times the injection capability from low Earth orbit of a launcher system, and in some cases more. Thus, an in-space refueling capability would make larger super heavy lift vehicles even more capable, and would enable smaller ones to inject from low Earth orbit a mass comparable to what larger launchers can do without in-space refueling. See Figure 5.2.1-1. In fact, the larger elements launched to low Earth orbit tend to be propulsion stages, and these are usually about 80% fuel by mass. If there were the capability to fuel propulsion stages in space, the single largest mass launched would be considerably less than in the absence of in-space refueling. The mass that must be launched to low Earth orbit in the current NASA plan, without the fuel on board, is in the range of 25 to 40 metric tons, setting a notional lower limit on the size of the super heavy lift launch vehicle if refueling is available. As an additional benefit of in-space refueling, the potential government-guaranteed market for fuel in low Earth orbit would create a stimulus to the commercial launch industry beyond the current International Space Station commercial cargo services market. The committee examined the current concepts for in-space refueling. There are essentially two. In the simpler one, a single tanker performs a rendezvous and docking with the EDS on orbit transfers fuel and separates, much like an airborne tanker refuels an aircraft. In a more evolved concept, many tankers rendezvous and transfer fuel to an in-space depot. See Figure 5.2.1-2, Artist's concept of a fuel depot servicing the Earth departure stage. Then at a later time, the EDS docks with the depot, fuels, and departs Earth orbit. The committee found both of these concepts feasible with current technology, but in need of significant further engineering development and in-space demonstration before they could be included in a baseline design. This would require engineering effort, and at some development investment, long-term life cycle savings may be obtained. The concept of in-space refueling introduces the idea of critical launches and less critical launches in any given mission. Using the lunar mission with crew as a reference, the critical launches would carry the Orion, Altair, and EDS to low Earth orbit. Depending on launch vehicle capacity, this could be accomplished on one flight as it was in Apollo, 2 or even 3 launches. Less critical missions would be the ones that bring fuel to low Earth orbit. The committee commissioned a detailed analysis of the reliability of missions that would require multiple launches of critical and less critical payloads. It found that achieving reasonable probability of mission success requires either 90-plus days of on-orbit life for the EDS or a depot, and that at most 3 critical launches should be employed. Since it is very constraining to balance mission components to always partition equally between launches, this strongly favors a minimum heavy lift capacity of roughly 50 metric tons that allows the flexibility to lift 2 dry exploration elements on a single launch. Another way to view the requirements of heavy lift is to consider the recurring cost to NASA of using a significant fraction of the yearly existing and planned U.S. launch capability after the shuttle retires. At reasonable production rates of the existing EELV heavy launch vehicles, mid-size EELVs, new commercial vehicles, and the Ares 1, much, if not all, of the excess capability that exists in the U.S. production system would be used launching 400 to 500 metric tons to low Earth orbit, and it would be an expensive way to accomplish this. The committee finds that exploration would benefit from the development of a heavy lift capability to enable voyages beyond low Earth orbit. This might be supplemented by the development of an in-space refueling capability. In-space refueling has great potential benefits, but needs development and demonstration before being incorporated into a baseline design. Using a launch system with more than 3 critical launches begins to cause unacceptably low mission launch reliability. Therefore, a prudent strategy would be to use launch vehicles that allow the completion of a lunar mission with no more than 3 launches without refueling. This would imply a launch mass to low Earth orbit of at least 65 to 70 metric tons based on current NASA lunar plans. Vehicles in the range up to about 100 metric tons will require in-space refueling for more demanding missions. Vehicle above this launch capability will be enhanced by in-space refueling but will not require it. When in-space refueling is developed, any of these launches will become more capable. The development of such a heavy-lift vehicle would have other benefits. It would allow large scientific observatories to be launched, potentially enabling them to have optics larger than the current 5-meter fairing sizes will allow. More capable deep space science missions could be mounted, allowing faster or more extensive exploration of the outer solar system. Heavy lift may also provide benefit in national security space applications. 5.2.2 The choices for heavy lift. The committee examined the 4 choices for heavy lift outlined in Figure 5.2-1 and Figure 5.2-2, all of which pose different heritage, capability, maturity, and organizational ramifications. They will be discussed with reference to the use on a typical lunar mission and a flexible path mission. Ares 5. The Ares 5 is used with a human-rated Ares 1 for lunar missions, the so-called 1.5 launch architecture. The Ares 1 launches the Orion, which docks in low Earth orbit with the Altair lander and EDS launched on the Ares 5. The Orion and Altair departs towards the Moon, propelled by the EDS. See Figure 3.4.2-1. The Ares 1 rocket is currently under development by the Constellation program and has a great deal of commonality with the Ares 5. This version of the Ares 5, in contrast with the Ares 5 Lite discussed below, is the most capable of the launch vehicle alternatives under study, with a payload to low Earth orbit of about 160 metric tons. See Figure 5.2.2-1. When used in conjunction with the Ares 1, the combined payload to low Earth orbit is about 185 metric tons. With an appropriately designed lunar lander, one Ares 1 and one Ares 5 land about 2 metric tons of cargo on the lunar surface of a human mission, and about 14 metric tons reaches the lunar surface on a cargo-only mission with a single Ares 5 launch. Both the Ares 1 and Ares 5 use solid rocket boosters, SRBs, a 5-segment SRB in the Ares 1 and a 5.5-segment SRB in the Ares 5. The Ares 5 first stage uses 6 engines from the RS-68 family. The engines are mounted on the bottom of a 10-meter diameter tank. The second, or Earth departure stage, is based on the J2X engine, which the Ares 5 shares in common with the Ares 1. The advanced RS-68 rocket engine of the core is a modification of the RS-68 engines used on the existing Delta IV launch vehicles. Certain changes to the RS-68 for use in the Ares family are anticipated. These include upgrades to reduce hydrogen flow at startup and for extended operation in the more aggressive Ares 5 thermal environment. The J2X rocket engine is a modification of the J2 engines used on the Saturn V program. The use of the Ares 1 as a means of crew transport to low Earth orbit will be discussed in Section 5.3. Ares 5 Lite. The Ares 5 Lite is a slightly lower performance variant of the Ares 5, with a low Earth orbit payload of about 140 metric tons, but with the same essential configuration as the Ares 5. However, in this option, it would be human-rated, as it is used for crew launch with the Orion. It uses 5-segment SRBs, already under development for the Ares 1, and 5 core engines, a derivative of the RS-68, the engine used on the Delta IV Heavy EELV. It would use a slight variant of the same EDS as the Ares 5, with the same J2X engine. For lunar missions, the Ares 5 Lite is used in the dual mode. The Orion and Altair are launched on separate Ares 5 flights, and they dock either in Earth or Moon orbit, depending on the mission mode eventually chosen. With a combined payload to low Earth orbit for the dual launches of about 280 metric tons, this architecture would enjoy considerable payload margin that could provide significant enhancement in mission robustness for lunar missions. With an appropriately designed lunar lander, this system lands about 7 metric tons of cargo on the lunar surface on a crewed mission. With a single Ares 5 Lite launch, the same lander can deliver about 14 metric tons on a cargo-only mission. When used on flexible path missions, a single Ares 5 Lite and EDS, in combination with the Orion and an in-space habitat, are able to support a visit to the Lagrange points without refueling. In order to reach near-Earth objects and beyond, in-space refueling, or alternatively multiple Ares 5 Lite launches, is necessary. Shuttle-derived launchers. The committee examined the shuttle-derived family, consisting of inline and side-mount vehicles substantially derived from the shuttle. These are all characterized by 4-segment solid rocket boosters, Space Shuttle main engines or their RS-25E expendable derivatives, and 8.3-meter diameter external tanks as used on the Space Shuttle. This class actually comprises a family of possible vehicles. Shuttle-derived side-mount launcher. On one end of the spectrum is the side-mount launcher that is most directly derived from the shuttle. See Figure 5.2.2-2. It replaces the shuttle orbiter with an expendable side-mounted payload carrier that contains both a clamshell-type payload shroud and a propulsion system consisting of 3 Space Shuttle main engines, SSME. It uses the exact same tank and SRB configuration as the shuttle. It would likely carry an EDS with a J2X engine internal to the payload bay. This would be the smallest development effort possible within the family. Depending on details of design, a side-mount launcher with an EDS can lift 90 to slightly more than 100 metric tons to low Earth orbit. Shuttle-derived inline launcher. At the other end of the spectrum is an inline vehicle such as the Jupiter 241, with 4 SSMEs mounted at the bottom of a redesigned tank thrust structure with an EDS atop the tank. See Figure 5.2.2-3. Once the existing stock of SSME engines is depleted, this configuration will use an expendable version of the SSME, the RS-25E. The upper stage uses liquid oxygen and liquid hydrogen as propellants, with a single J2X rocket engine. The committee evaluated the smaller Jupiter 130 that does not have an EDS, but used the more capable Jupiter 241 as the basis of comparison, which has a launch capacity in the range of 100 to 110 metric tons to low Earth orbit. In a lunar exploration scenario, it is assumed that 3 shuttle-derived launchers of a nominal 110 metric ton capability would be used for a crewed mission. A single launcher would be used for lunar cargo missions. When used in conjunction with a lunar lander designed for this size vehicle, this system lands about 5 metric tons of cargo on a crew mission. A single launch cargo mission lands less than 5 metric tons of cargo on the lunar surface. However, a single launch cargo mission enhanced by the use of in-space refueling increases the cargo mass landed on the lunar surface to more than 20 metric tons. For flexible path missions, 2 shuttle-derived launchers, combined with in-space refueling of an EDS, are required to propel the Orion and in-space habitat to the Lagrange points, near-Earth objects, and beyond. While the committee did not examine the technical trade between the side mount and inline variants in detail, it observes that the side mount variant is considered an inherently less safe arrangement if crew is to be carried, and is more limited in its growth potential. EELV Heritage Super Heavy. The EELV Heritage Super Heavy launchers represent a potential family of vehicles derived from the current Evolved Expendable Launch Vehicles heritage. They are distinguished technically from the NASA Heritage vehicle by their use of liquid booster rather than solid rocket boosters, and secondarily by a hydrocarbon RP-1 fueled rocket in the first stage core. See Figure 5.2.2-4. The upgraded EELV systems would have a core vehicle that would by itself have a launch capability to low Earth orbit in the range of 30 to 35 metric tons. Using a super heavy variant that would have a core and 2 boosters of the same basic design, and when used in conjunction with an upgraded common hydrogen-oxygen upper stage, it is likely to have a maximum payload to low Earth orbit in the range of 75 metric tons. This exceeds the nominal minimum for a heavy lifter useful for exploration as defined above. A representative of this category of launchers is the Atlas V Phase II Heavy. The EELV Super Heavy uses 2 RD-180 rocket engines on each of the core and 2 boosters. The RD-180 engine has a long history of successful launches in Russia and in the U.S. on the Atlas V family of launch vehicles. The upper stage uses liquid oxygen and liquid hydrogen as propellant, with 4 RL-10 rocket engines. The RL-10 family of engines has a long history of successful launches on programs including the Titan, Atlas, and Delta families of vehicles. The Atlas Phase II is a proposed follow-on of the EELV program, with larger 5-meter diameter stages manufactured using the existing 5-meter production facilities that currently produce the Delta IV core stages. When used in conjunction with flexible path missions, the EELV Heritage Launcher and EDS send the Orion and in-space habitat towards the Lagrange points, near-Earth objects, and beyond, with 2 launches plus in-space refueling. Developmental considerations. Any of these launcher options will entail a substantial development project. The committee observes that throughout the history of launcher development, and particularly for the shuttle, the aim has frequently been to design for ultimate performance, often at the cost of reliability and operational efficiency. In particular, NASA's design culture has repeatedly focused on maximizing performance at minimum development cost, generally resulting in high operational and life cycle costs. While performance is important in launchers, good performance margins and associated robustness are also desirable and can lead to lower life cycle costs. A shift in NASA design culture toward design for minimum life cycle cost, accompanied by robustness and adequate margins, will allow NASA programs to be more sustainable. There is one additional consideration regarding heavy lift capability. In all missions beyond low Earth orbit, there will be a need for 1 or 2 additional propulsive maneuvers far from Earth. For example, in visiting the Moon, a burn is necessary to enter lunar orbit and another to leave. When visiting a near-Earth object, a burn is necessary to decelerate to rendezvous with the object, and then a second to return to Earth. Exploration will require a long-duration in-space restartable stage. This would become a building block of exploration propulsion systems, potentially including the lunar descent stage. Findings on launch to low Earth orbit and beyond. The need for heavy lift. A heavy lift launch capability to low Earth orbit, combined with the ability to inject heavy payloads away from the Earth, is beneficial to exploration and will also be useful to the national security, space, and scientific communities. The committee reviewed the Ares family of launchers, shuttle-derived vehicles, and launchers derived from the EELV family. Each approach has advantages and disadvantages, trading capability, life cycle costs, operational complexity, and the way of doing business within the program and NASA. In-space refueling. The ability to add fuel to an Earth departure stage, either from in-space docking with a tanker or from a depot, is of significant potential benefit to the in-space transportation system beyond low Earth orbit. The technology for in-space refueling is available, but a further development and demonstration program is required. Therefore, a prudent approach is to develop a heavy-lift launch system with sufficient capabilities for early missions, which would later be enhanced by in-space refueling when it becomes available. Sustainability of operations of U.S. launch systems. NASA's design culture emphasizes maximizing performance at minimum development cost, repeatedly resulting in high operational and life cycle costs. A shift in NASA design culture toward design for minimum discounted life cycle cost, accompanied by robustness and adequate margins, will allow NASA programs to be more sustainable. In-space propulsion. For almost all foreseeable missions beyond low Earth orbit, there is a need for one or two propulsive maneuvers, often after weeks or months in space. Efficient engines and stages with high reliability restart capability will need to be developed. End of Section 11. Recording by Maria Casper. Section 12 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 5.0 Launch to Low Earth Orbit and Beyond, Part 2. 5.3 Crew Launch to Low Earth Orbit. Among the most safety-critical aspects of human spaceflight is the delivery and return of crew to and from low Earth orbit. The fourth key question examined by the committee is, how should U.S. crew be transported to low Earth orbit? There are two choices for transporting U.S. crews to and from low Earth orbit that emerged from the work of the committee: a government-provided and operated system and a commercially provided crew delivery service. This discussion assumes that the Orion vehicle will be the primary U.S. capsule for crew transportation beyond low Earth orbit and re-entry into Earth's atmosphere upon return from these voyages. 5.3.1 Ares 1 plus Orion, government-provided crew to low Earth orbit. The current NASA plan for crew transport to low Earth orbit, comprising the Ares 1 launch vehicle and the Orion crew capsule, was selected in 2005 as part of the ESAS study, based in part on the anticipated availability and projected crew safety considerations of the Ares 1 and Orion. At the time of ESAS, estimates showed that Ares 1 and Orion would be available for crew transport service to the International Space Station by 2012. The date projected by the Constellation program is now 2015. As the plan evolved after 2005, the Ares 1 developed increasing commonality with the Ares 5, providing architectural synergy and reducing development costs of the family. Ares 1. The Ares 1 launch vehicle currently consists of a single 5-segment solid rocket booster as the first stage and a liquid-fueled upper stage. See Figure 5.3.1-1. The 5-segment SRB is a modification to the existing Space Shuttle SRBs. The upper stage uses liquid oxygen and liquid hydrogen as propellants with a single J2X rocket engine. The J2X rocket engine is a modification of the J2 engine used on the Saturn V program. In its selection of a crew launch system, ESAS correctly placed a very high premium on crew safety, and the Ares 1 was selected because of its potential delivering at least 10 times the level of crew safety as the current shuttle. The launch vehicle configuration is one that best allows for crew escape in the event of a launch failure. The capsule is mounted at the top of the stack and has an independent launch escape system. The track record of demonstrated high reliability of the SRB suggests a low likelihood of first-stage failure on ascent. Under the budget profile NASA leadership anticipated in 2005, estimates showed that the Ares 1 could be developed by the early to mid part of the decade, and the Ares 5 could be developed by the late 2010s. It was thought that the Ares 1 would have a lower operating cost when visiting the International Space Station than other alternatives, and would produce a lower operating cost of the entire system when joint operations of the Ares 1 and Ares 5 were begun. Additionally, the development approach of engaging many NASA employees in the design and testing of the Ares 1 would allow the NASA workforce, which has not developed a new rocket for over 20 years, to gain experience on the relatively simpler Ares 1 rocket before beginning the development of the more complex Ares 5. 5.3.2 Alternatives to government-provided crew access to low Earth orbit. The committee considered several alternatives to Ares 1 and Orion, including a longer-term reliance on international, currently Russian, crew transport services, the human rating of an existing EELV for launching the Orion, the development of commercial crew transport services, the use of a heavy lift vehicle to launch the Orion. While the committee found interim reliance on international crew transport services acceptable, it also found that an important part of sustained U.S. leadership in space is the operation of our own domestic crew launch capability. This closed out the first alternative. The committee next examined a NASA-commissioned study by the Aerospace Corporation on the feasibility and cost of human rating an EELV, the Delta IV Heavy, for use as the launcher for Orion. Delta IV HLV. The Delta IV Heavy launch vehicle consists of 2 liquid-fueled strap-on boosters, a liquid-fueled first stage and a liquid-fueled upper stage. The 2 strap-ons and the core stage are very similar and use liquid oxygen and liquid hydrogen as propellants, and a single RS-68 family rocket engine on each of the 3 stages. The independent study found that launch of Orion to low Earth orbit did not require an upper stage, as the spacecraft could provide the necessary impulse. The Delta IV HLV is a variant of one of the EELVs that has launched successfully many times. While launch of the Orion on the Delta IV HLV was found to be technically feasible, It requires some modification of the current launcher and was comparable in cost and schedule to simply continuing with the development of the Ares 1. When the committee factored in the carrying cost of the NASA infrastructure that would be maintained if any NASA heritage heavy launcher would eventually be developed, Ares 5 in any variant or a more directly shuttle-derived heavy launcher, any cost savings that might have occurred due to using an EELV to launch the Orion were lost. Using the EELV for launch of Orion would only make sense if it were coupled with the development of an EELV heritage super heavy vehicle for cargo launch. Except in this case, this analysis closed out the second option. 5.3.3 Commercial services to transport crew to low Earth orbit. Having eliminated the long-term international supply option and the EELV option for all but the EELV heritage super heavy choice for heavy lift, the remaining possible choices besides Ares 1 were to utilize commercial crew services or use the heavy lift vehicle as a crew launcher. As the nation moves from the complex reusable shuttle back to a simpler, smaller capsule, it is an appropriate time to consider turning this transport function over to the commercial sector. There is broad policy support for this approach, from both congressional legislation and presidential policy, see Figure 3, and one of the four main charges given to the committee by the Office of Science and Technology Policy in its statement of task was to stimulate commercial spaceflight capability. This section considers the technical feasibility of a commercial service, safety issues, financial implications, programmatic risks, and acquisition strategy. Technical feasibility of commercial transport services for crew. The committee examined the technical feasibility of utilizing a commercial service to transport crew to low Earth orbit. First, it is a statement of fact that all of the U.S. crew launch systems built to date have been built by industry for NASA. The system under contemplation is not much more complex than a modern Gemini, which was built by U.S. industry over 40 years ago. It would consist of a 3 or 4 person crew taxi launched on a rocket with a launch escape system. It would have an on-orbit life independent of the International Space Station of only weeks, but potentially be storable at the International Space Station for months. Such a vehicle would re-enter the Earth's atmosphere from the speed of orbital flight rather than the significantly higher speed for which Orion is designed. Its smaller size makes possible the option of landing on land, potentially reducing operations cost when compared to a sea landing. Recently, several aerospace companies began developing new rockets and on-orbit vehicles as part of the commercial cargo delivery program. Several other U.S. companies are contemplating orbital passenger flight. There is little doubt that the U.S. aerospace industry, from historical builders of human spacecraft to the new entrants, has the technical capability to build and operate a crew taxi to low Earth orbit. NASA's role in safety and mission assurance. The committee treated the safety of crew vehicles as the sine qua non of the human spaceflight program, and would not suggest that a commercial service be provided for transportation of NASA crew if NASA could not be convinced that it was substantially safe. The critical question is, can a simple capsule with a launch escape system operating on a high-reliability liquid booster be made safer than the shuttle and comparatively as safe as Ares 1 plus Orion? An important part of this analysis rests on the reliability of the launcher. Thus, commercial crew launchers based on high-reliability vehicles that already have significant flight heritage or will develop flight experience soon would be more obvious candidates as a crew launcher. Ares 1 has a heritage that traces to the use of the SRBs on the shuttle. but other potential crew launchers can also trace their lineage to significant flight heritage. Given the history of human spaceflight, putting commercial crew transport to space in the critical path of any scenario represents a major shift in policy. As will be discussed in Section 5.4.2, the committee reviewed convincing evidence of the value of independent oversight in the mission assurance of launchers, and would envision a strong NASA oversight role in assuring commercial vehicle safety. The challenge of developing a safe and reliable commercial capability for crew transport will require devoting government funds to buy down a significant amount of the existing uncertainty. Whatever the particulars of this risk removal process, it will take an appreciable period of time and require the application of thorough, independent mission assurance practices. A critical aspect of this exercise will be confirming the root cause and adequacy of correction of any failures or anomalies encountered in the development test program. Thus, the committee views any commercial program of crew transport to the International Space Station as involving a strong independent mission assurance role for NASA. The committee identified elements of a plan that would lead to the creation of a commercial service for crew transport, building on NASA incentives and guarantees. This included an assessment of the financial aspects and benefits of commercial crew services, the programmatic risks of relying on commercial crew services, and potential mitigation strategies, and an approach to engaging the commercial community in this program. Financial aspects of the commercial crew services. The committee engaged in a two-step process for assessing the potential financial benefit of commercial services for crew transport. This involved both estimating the cost to develop and operate the system, and then determining what fraction of this cost NASA would likely have to provide as an incentive to industry to enter into this venture. During its fact-finding process, the committee received proprietary information from 5 different companies interested in the provision of commercial crew transportation services to low Earth orbit. These included large and small companies, some of which have previously developed crew systems for NASA. The committee also received input from prospective customers, stating that there is a market for commercial crew transportation to low Earth orbit for non-NASA purposes if the price is low enough and safety robust enough, and from prospective providers stating that it is technically possible to provide a commercially viable price on a marginal cost basis given a developed system. None of the input suggested that at the price obtainable for a capsule plus expendable launch vehicle system, the market was sufficient to provide a return on the investment of the initial capsule development. In other words, if a capsule is developed that meets commercial needs, there will be customers to share operating costs with NASA. But unless NASA creates significant incentives for the development of the capsule, the service is unlikely to be developed on a purely commercial basis. The committee then estimated the cost to NASA of creating an incentive for industry to develop the commercial transport capability for crew. This would probably be a significant fraction, but not the entirety of the cost of such a development. Given a properly structured procurement, estimates the committee received from potential providers for the price of reaching initial demonstration flight of a crew taxi capsule ranged from $300 million to $1.5 billion. For estimating purposes, the committee assumed that 3 contracts were initiated and 1 competitor subsequently dropped out, suggesting an expected cost to NASA of between $2 billion and $2.5 billion. In addition, the committee believes that if a commercial crew program is pursued, NASA should make available to bidders a suitable version of an existing booster with a demonstrated track record of successful flight, adding to the program cost. The best preliminary estimate of the committee was about a $3 billion program for the fraction of the design, development, test, and evaluation effort that would be borne by NASA. After multiplying by the historical growth factors and other multipliers associated with 65% confidence estimating, as will be discussed in Section 6.3, the cost carried in the committee's final estimate of the cost of the program to NASA is about $5 billion. Comparing the scope of providing a commercial crew capability to the cost of historical programs offers a sanity check. In the existing COTS-AC contracts, 2 commercial suppliers have received or invested about $400 to $500 million for the development of a new launch vehicle and unmanned spacecraft. Gemini is the closest historical program in scope to the envisioned commercial crew taxi. In about 4 years in the early to mid-1960s, NASA and industry human-rated the Titan II, which required 39 months, and designed and tested a capsule. In GDP inflator-corrected 2009 dollars, the design, development, test, and evaluation cost of this program was about $2.5 to $3 billion, depending on the accounting for test flights. These 2 comparatives tend to support the estimate that the program can be viable with a $5 billion stimulus from NASA. The committee considered several other factors that would support this estimate of the incentive cost to NASA. If this is to be a commercial venture, at least some commercial capital must be at risk. Alternate sources of capital, including private and corporate investment, would be expected. Next, the committee considered the cost associated with the development of a relatively simpler launcher and capsule designed only as a low Earth orbit crew taxi in comparison with those associated with the far more capable Ares 1 and Orion. Additionally, the committee heard many argue that economic efficiencies could be found by striking a better balance between the legitimate need for a NASA quality assurance and safety process on one hand, and allowing industry to execute design and development efficiently on the other. Significantly, the committee considered the fact that some development costs and a larger fraction of operating costs of a commercial crew service to low Earth orbit could be amortized over other markets and customers. This is more obvious for the launcher, which potentially could also be used for the existing markets of International Space Station cargo to low Earth orbit, science and national security space satellite missions, and commercial satellite launches. In the future, the commercial booster used for crew might also launch fuel to low Earth orbit for in-space refueling, and it might carry additional non-NASA crew flights. The non-NASA markets and customers for the capsule are less easily quantified. It is possible that other governments would procure crew launched to International Space Station from a U.S. commercial provider, and that private travel to low Earth orbit could be more common by the latter part of the decade. Note that if there were only one non-NASA flight of this system per year, it would reduce the NASA share of the fixed recurring cost by 33%. It was estimated by the committee that under the less constrained budget, to be discussed in Chapter 6, the commercial crew launch service could be in place by 2016. Estimates from providers ranged from 3 years to 5 years from the present. Assuming a year for program realignment, this would produce a start in early fiscal year 2011. Using the upper end of the estimated range, a capability in 2016 could be estimated with reasonable confidence. Programmatic risks of commercial crew to low Earth orbit and potential mitigations. The committee recognizes that the development of commercial services to transport crew come with significant programmatic risks. Among these are that the development of this capability will distract current potential providers from the near-term goal of successfully developing commercial cargo capability. Second, the commercial community may fail to deliver a crew capability in mid-program, and the task would revert to NASA. This could be caused by either a technical failure or a business failure, a failure to obtain financing, changes in markets or key suppliers, realignment of business priorities, or another non-technical reason. Either type of failure would require NASA intervention, and the possibility that NASA would either have to operate the system or fall back to an alternative. While there are many potential benefits of commercial services that transport crew to low Earth orbit, there are simply too many risks at the present time not to have a viable fallback option for risk mitigation. The committee contemplated several alternatives, including continuing to rely on international providers, likely available but not consistent with the long-term need for U.S. access as part of its leadership in space, and continuing the Ares 1 program in parallel, prohibitive in terms of cost. The committee also considered the possibility of putting the Ares 1 program on warm hold, ready for a possible restart, while continuing the development of the 5-segment SRB and the J2X, which are common to the Ares 5. In the end, the committee thought that the most cost-effective fallback option that would move NASA most rapidly toward exploration is to continue to develop the Orion and move as quickly as possible to the development of a human-rateable heavy lift vehicle. See the discussion in Section 5.3.4 on human rating. The first stage of any of the heavy lift launchers under consideration would be more than capable of launching an Orion to low Earth orbit. In the best case, the heavy lift vehicles themselves would not be available until the beginning of the 2020s, but the first stage, or core, could be accelerated, perhaps by a year or two. In this case, the core heavy human-rated launcher would arrive only a few years later than an Ares 1 under the less constrained budget scenarios. The details of the preferred fallback option are best left to NASA, but the question is clear. Assume that emphasis will be placed on building the heavy lifter as quickly as possible, and assume that commercial services for crew transportation to low Earth orbit will be started in development and may fail to materialize. What variant of the heavy launcher can be identified that could be developed quickly and at small marginal cost in the future, if needed, to transport Orion and crew to low Earth orbit? A desirable feature is that the preparation for the development of this variant would have the minimum impact on the construction of the heavy lift vehicle itself. Engaging the commercial community in crew transport services. The potential providers of capsules emphasized that the nature of the acquisition of these services is critical. To be commercially viable, low operating cost is essential, and to obtain that cost, the requirements for the capsule need to be as few as is essential and stable. Several providers gave anecdotal examples where NASA programs suffered from significant requirement creep and emphasized the need for a more commercial-type procurement, where any changes to work scope would be matters for mutual negotiation rather than one-sided impositions by NASA. The committee envisions a new competition for this service, in which both large and small companies are invited to participate. Several potential providers should be funded through some initial development milestones measuring tangible progress and incrementally incentivized. It is crucial to the success of the program that multiple providers be carried through to operational service. It is the pressure of competition that provides the drive for low operating cost. Assurances of a market would need to be offered by the government. By creating a third market for commercial launch services, cargo to International Space Station, fuel to low Earth orbit, and crew to low Earth orbit, it is possible that the efficiencies associated with increased production runs and more frequent operations will appear. 5.3.4 Human rating of launchers. The history of human rating U.S. launch vehicles can be traced to the Atlas and ICBM Titan usage in the Mercury and Gemini programs. The purpose of human rating was and is to assure that safety levels are appropriate for human flight. Crew safety was addressed in these earlier programs primarily by adding a crew escape system. The reliability of these launch vehicles was addressed by eliminating known design weaknesses, adding redundancies, providing fault detection systems to initiate crew escape, and tightening requirements for manufacturing, assembly, systems test, and checkout at launch sites. The process of human rating launch vehicles is central to the viability of commercial service for crew transport, as well as the option of using the heavy launcher as a backup. The committee found a progressive new approach to human rating at NASA, reflected in the current human rating guidelines, NASA Procedural Requirement 8705.2b. These guidelines, applicable to newly developed NASA vehicles, provide for intelligent application of similar and dissimilar redundancy when called for, and appropriate approaches to single-string design when unavoidable. In addition, there is a general set of guidelines, NPR 8715.3, that currently would be applied to NASA personnel operating in non-NASA vehicles. In view of the complexity and cost of retroactively human rating a vehicle, comparable to a significant fraction of the original cost to develop the vehicle, the committee suggests that all new NASA-developed vehicles, including heavy-lift launchers, be designed so that they are human-ratable. That is, they could reasonably be human-rated at some point in the future. This is a compromise between human-rating them at inception and not human-rating them at all. It preserves the option to human-rate in the future at lower cost. NASA would benefit from this approach so that it could use its heavy-lift launcher as a backup crew vehicle with Orion should the commercial providers fail to deliver for any combination of business and/or technical reasons. Additionally, the criticality of cargo launched on the heavy-lift vehicle would suggest that NASA institute quality control and requirements comparable to human rating guidelines in any event. Findings on crew launch to low Earth orbit. Note: a finding on the Ares 1 is presented in Chapter 4. End note. The need for independent U.S. human access to space. In the long run, it is important for the U.S. to maintain independent access to low Earth orbit for its crews. In the future, this might be provided by government, commercial providers, or a combination of the two. Commercial launch of crew to low Earth orbit. Commercial services to deliver crew to low Earth orbit are within reach. While this presents some risk, it would provide an earlier capability at lower initial and life cycle costs than government could achieve. A new competition with adequate incentives should be open to all U.S. aerospace companies. This would allow NASA to focus on more challenging roles, including human exploration beyond low Earth orbit, based on the continued development of the current or modified Orion spacecraft. Human rating of launch vehicles. NASA has recently adopted a new, more outcome-based standard for human rating space systems, and has in its policy a more flexible approach for human rating existing or new third-party systems. NASA would be well served by applying these policies to field a set of safe yet efficient capabilities, including the provision that all newly developed government-funded launch vehicles be readily human-ratable. In this way, if plans change in the future, for example, if the commercial capability of crew transport to low Earth orbit fails to materialize, NASA would have a backup means of launching crew on heavy-lift vehicles. Safety. Human space exploration is an inherently risky endeavor. NASA should continue to make every reasonable effort to reduce the risks of spaceflight, Design for safety should be the prime, but not only, criterion in the development of systems and operations. 5.4. Additional issues in launcher selection. 5.4.1. Launch vehicle performance and costing. In evaluating the systems described in this chapter, the committee noted that each has avid proponents, and as such, the claimed cost, schedule, and performance parameters include varying degrees of aggressiveness. Some of these estimates are close to or within the spread of historical programs, while others are well outside historical bounds. The latter could, of course, be attributed to fresh new approaches that make the historical databases inapplicable, or they could be attributable to unwarranted optimism. The analysis techniques employed in the assessment sought to differentiate between the two. The only large potential decrease to the cost of space transportation, absent greatly increased traffic, resides in the adoption of a new paradigm for commercially purchasing highly reliable space transportation services. This approach benefits from commercial best practices embraced by experienced providers of launch systems and new systems and processes offered by young firms. The price of shifting to commercial practices is to decrease the NASA workforce and sacrifice the expertise that has been built up at NASA over the years, as the agency has directed and overseen the development of launch systems. This new strategy may eventually restore the total number of space launch workforce in terms of expertise and number of workers, but near-term reductions would be expected. The health and viability of the large solid rocket motor industrial base rests in part on the choice of future crew transport and heavy-lift cargo launch system designs. Those that are all liquid obviously present the most negative impact on the SRM industrial base, and those that either launch crew with an SRM or support heavy lift with SRMs provide the most benefit to the SRM industrial base. If the choice is to pursue all liquid launch systems for both crew and cargo, there is no perceived future need for large segmented SRMs in support of civil space activities. 5.4.2. Reliability. Reliability of launchers is important to the safety of crew and the success of missions or exploration. The U.S. history of heavy lift launcher reliability is shown in Figure 5.4.2-1. The historical record can be separated into two classes, those intended for human spaceflight and those intended for cargo use. Saturn and the Shuttle are in the former class, while the other existing vehicles considered here are in the cargo class. The most reliable U.S. heavy-lift launch vehicle built to date is the Shuttle, whose launch reliability, demonstrated by flight history and computed using the Bayesian estimation process, based on a 50% confidence level common for this type of analysis, is 98.7%. The Saturn vehicles also exhibited high reliability over their limited flight history. The less reliable Titan HLV only launched cargo, and the Delta IV-H is limited to only 3 flights to date. During this examination of future space exploration launch systems, the vehicles considered included those derived from Shuttle, Saturn, and Delta IV Heavy Heritage engines and motors, including Ares 1 and 5 and Shuttle derivatives, those derived from the EELV program families of launchers, Atlas V and Delta IV, and new vehicles with limited heritage, Falcon and Taurus II. Historically, vehicles with heritage derived from prior demonstrated systems have shown greater reliability in early usage than newly developed systems. The process of converting an established cargo launcher into a human-rated launcher results in improved reliability, as was demonstrated in the early U.S. human spaceflight programs where modified ICBMs were employed as launch systems. History has shown that the early flight period is of much higher risk than would be expected later in flight history. Figure 5.4.2-2 displays flight reliability for programs managed by the U.S. government, those managed by foreign governments, and those managed by commercial providers. It should be noted that all of the U.S. vehicles have in large part been engineered and manufactured in industry, and that the so-called commercial vehicles were originally developed and produced under government Air Force contracts. Importantly, the latter began as ICBMs, and unlike the government launch vehicles category, are not human-rated. Space launch vehicles have a history of malfunctions caused by human pre-flight technical error rather than so-called random part failure or in-use operator error. This is clearly demonstrated in Figure 5.4.2-3, which shows the root cause of flight malfunctions derived from all U.S. heavy-lift launches to date. Included in the data are the results of process and design errors associated with the shuttle thermal protection system and SRB joint gas anomalies that were observed, but were not viewed as hazardous prior to the failures of Challenger and Columbia, respectively. Although some thermal protection system anomalies continue to occur, SRB joint gas leaks, which had been a recurring problem with the large segmented solid motors, have been significantly less prevalent after the design changes following the Challenger failure. Summary. There are many issues that must be carefully considered leading to the final decisions on the launch system for both heavy cargo and crew. These include, but are not limited to, the cost, schedule, and performance of the launch system, the likelihood that an increase in volume of production and operation, including by other customers, will decrease costs in the future, the impact on the present and future industrial base, the initial and ultimate reliability of the launcher, and the extent to which the heritage of the launcher influences the early operational reliability, the benefit of independent assurance in increasing the demonstrated reliability, the root cause of failures of launchers, and the extent to which these can be modeled and controlled by sound practices in design and processing. End of Section 12. Recording by Maria Casper.
Section 13 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of the U.S. Human Spaceflight Plans Committee. Chapter 6, Program Options and Evaluation, Part 1. This chapter presents a synthesized set of options for the future of U.S. human spaceflight. Section 6.1 presents the evaluation criteria the committee developed. The 5 key questions that framed the examination are briefly restated in Section 6.2, and the choices for each are summarized. These have been presented individually in Chapters 3, 4, and 5. In Section 6.2, pointers denote places where the individual choices will be discussed in the context of the integrated options. These analyses form the basis of sections 6.3 through 6.6. These integrated options tie together choices from the 5 key decisions to allow cost and schedule to be assessed, and an overall evaluation of progress to be made. 6.1 Evaluation Criteria. In order to conduct an independent review of ongoing U.S. human spaceflight plans and alternatives, the committee recognized that it would be important to define a process that would equitably evaluate the wide range of options to be identified. Consistent with the systems engineering approach, it was important to clearly define the set of criteria against which all options would be assessed, and to define an evaluation process that would enable a fair and consistent assessment of each option. Since many of the evaluation criteria are not quantitative, the committee did not intend that the evaluation would generate a single numerical score. Rather, it would provide a basis for comparison across options, highlighting the opportunities and challenges associated with each. Assigning weights to individual figures of merit is within the purview of the ultimate decision makers. In order to identify integrated options that are safe, innovative, useful, affordable, and sustainable, the committee developed a number of evaluation criteria by which the relative merits of various human spaceflight missions and objectives could be compared. The committee was chartered by the Office of Science and Technology Policy in the Executive Office of the President. The committee's statement of task, see Appendix C, provided important guidance. The committee considered metrics suggested by its members, as well as those based on previous reviews and studies, such as the 1991 Synthesis Group, as well as those derived from policy and historical documents, including the Space Act of 1958 and the 2004 Vision for Space Exploration. There were numerous challenges in evaluating the complex set of integrated options considered for human spaceflight because they vary widely with respect to three principal dimensions. Benefits to shareholders. The community of stakeholders is diverse, and the potential benefits are equally wide-ranging. Stakeholders include the U.S. government, the American public, the scientific and education communities, the industrial base and commercial business interests, and human civilization as a whole. Each option offers benefits to some subset of stakeholders, nations, and humankind. These benefits include the capability for exploration, the opportunity for technology innovation, the opportunity to increase scientific knowledge, the opportunity to expand U.S. prosperity and economic competitiveness, the opportunity to enhance global partnerships, and the potential to increase the engagement of the public in human spaceflight. Risk. Each benefit has associated risks. There is uncertainty about the level of benefit that will actually be achieved, since attaining some of the goals may take decades. These risks are not independent of each other. NASA can mitigate some, but others are driven by external forces. Good program management can ameliorate schedule and programmatic risk, given sufficient schedule margin and financial reserves. Safety and mission risk can be managed by changing the mission profile or reducing program content. Programmatic sustainability is a key concern, since any change to the human spaceflight program is likely to affect existing contractual agreements and will require long-term commitments beyond the term of any one presidential administration. There is also risk to the nation's workforce and capabilities in critical skills. Currently, NASA's workforce represents expertise and experience that have enabled its outstanding achievements in space. The industry workforce is fragile because once the need for a capability stops, marketplace pressures will diminish it, and reconstituting it may be very difficult and extremely costly. Budget realities. The desire to identify options that will fit within the existing budget is a significant constraint. Ultimately, only the President and Congress can determine what is affordable in the context of other major national financial demands. Human spaceflight is not a short term commitment, and it requires budget stability for decades in order to achieve its goals. Year to year funding will affect NASA's ability to successfully implement strategic decisions that can reduce total life cycle cost. The committee recognizes that operating costs have a sustained and significant impact on the budget, and they may limit the ability to start new efforts critical to achieving human spaceflight goals. For the purpose of this assessment, the committee chose to represent the full cost of the programs and did not assume any financial contributions by international partners. These dimensions were expanded into 12 criteria by which integrated options could be compared. The committee clearly recognized that for each option there is some degree of uncertainty as to the magnitude of the influence and interdependence across the three dimensions. The committee selected the following criteria as the basis for evaluation. Exploration preparation. 1. Exploration preparation. Since the nature of exploration is, by definition, uncertain and subject to the surprise of discovery, it is important to establish a robust program that provides the opportunity to demonstrate technology, systems, and operations that will be important in future exploration. Specifically, a program that can be adapted to explore destinations that facilitate missions to Mars. 2. Technology innovation. Integrated options should enable technology maturation and foster the development of new modes of exploration, in addition to creating new technologies and new engineering knowledge that will enhance exploration. Technology development should also provide the opportunity to demonstrate national leadership in innovation. Technologies that are of use to stakeholders beyond NASA can be critical to the nation as a whole and should be sought during the exploration effort. 3. Science knowledge. Integrated options should address research areas critical to the scientific community as defined by the National Academy's Decadal Survey priorities. They should include an implementation plan that supports accomplishment of the prescribed research as a key product of the mission. The committee recognizes that for some decadal survey priorities, the requirement for the human spaceflight program is simply to do no harm. However, science can be enhanced by human exploration, particularly of complex environments, and by providing the ability to service scientific facilities in space. 4. Expanding and protecting human civilization. Integrated options should lead to the possibility of a sustained and off-planet human presence. They should also support research for physiological effects associated with radiation and zero or low G, as well as physiological stress associated with long duration remote exploration. Finally, An option is more highly rated if it will aid in the protection of human civilization against a near Earth object impact. 5. Economic expansion. Integrated options should encourage and stimulate a growing profitable industrial base. They should provide an opportunity for a sustained commercial engagement, and they should help increase U.S. development and production capabilities. Those capabilities would, in turn, increase the nation's international competitiveness, as well as ultimately lower the cost of space transportation and operation. 6. Global partnerships. Integrated options should provide the opportunity to strengthen and expand international partnerships in the human spaceflight program. These would include existing international partners, but should not preclude expansion to new partners and would allow partners to make contributions that could be on the critical path to mission success. Participation by other countries would be advantageous not only from the perspective of encouraging global cooperation, but also in terms of creating opportunities for synergistic research, risk reduction, cost sharing, and technology interchange. 7. Public engagement. Integrated options should inspire current and future generations, educate the public about the opportunities and societal benefits gained from space missions, and motivate young people to pursue an education in science, technology, engineering, and mathematics, followed by careers that capitalize on this education. Options that provide the opportunity for regular visible accomplishments can galvanize broad public interest in exploration. 8. Schedule and programmatic risk. Integrated options should be formulated to deliver a stated exploration capability on schedule. The technical design should be robust, and technologies required should be reasonably mature, with sufficient schedule and technical margins to support risk mitigation. 9. Mission safety challenges. The committee did not carry forward any integrated option that failed to provide for reasonable crew safety and overall mission success. Therefore, to discriminate among options, the committee assessed the relative risk and complexity of mission scenarios and the likely impact on crew safety and mission reliability. Human exploration beyond low Earth orbit will be riskier than current human spaceflight activities, since such exploration requires doing things that have not been done before, and the options for recovery will be limited. Missions that involve beyond lunar landings, beyond near Earth orbit flybys, or complex orbital operations will have mission profiles with a significantly increased safety challenge. 10. Workforce impact. The committee evaluated the impact on the workforce in two ways. 1. The impact on national critical skills, and 2. The impact on the total NASA and industrial workforce. Each option was assessed for its potential impact on the critical skills across the nation and the ability to retain or develop the needed critical skills and expertise needed both in industry and at NASA. The impact on the total workforce is an assessment of the potential for reduction of employment as a function of the dollar investment in human spaceflight. 11. Programmatic sustainability. Integrated options should have a broad base of support for ongoing future funding. They should have a manageable impact on pre-existing contracts and enable a smooth transition from current human spaceflight operations. Support and advocacy for the option could come from other governmental agencies, space-related organizations, industry, and Congress. 12. Life cycle cost. The FY 2010 budget for NASA's future human exploration programs, including operation costs through 2020, is roughly $99 billion. The committee was tasked to provide at least two options within this budget profile, and if appropriate, provide options that are somewhat less constrained. Clearly, a program that meets the current budget with high value in other categories would be the ideal in complying with the committee's charter. The committee deliberated at length in public meetings about the advantages and disadvantages of each option with respect to these 12 criteria. Wherever possible, quantitative analytical assessments were utilized to inform the ratings. In the end, however, it was usually necessary to interpret the available information through the considered judgments of the 10 members of the committee, based on their experience in space matters. The results were captured using a score of -2, least benefit, -1, 0, 1, or 2, most benefit, for each attribute of each integrated option. 6.2. Key decisions and integrated options. 6.2.1 Key decisions. The future of U.S. human spaceflight in the upcoming decades can be formulated in terms of 5 key questions and the associated choices for answering each one. The questions outlined in Chapter 1 and discussed further with potential answers in Chapters 3, 4, and 5 are: 1. What should be the future of the Space Shuttle? Prudent fly out of remaining flights, currently part of NASA's policy, but FY 2011 funding is not part of the President's budget. Extend shuttle through 2015 at minimum flight rate, only likely in conjunction with extending the ISS and developing a directly shuttle-derived heavy lift vehicle. This question will be examined in Section 6.4, in which some integrated options extend the shuttle life and others do not. 2. What should be the future of the International Space Station, ISS? Terminate U.S. participation in the ISS by the end of 2015. Continue U.S. participation through at least 2030, probably at an enhanced level of U.S. utilization. This decision will be discussed in Section 6.4, in which some integrated options extend the utilization of the ISS by the U.S. and others do not. 3. On what should the next heavy lift launch vehicle be based? Ares 1 plus Ares 5. Ares 5 Light dual launch with no refueling required for lunar missions, but enhanced with, potentially commercial, refueling for more demanding missions. Directly shuttle-derived vehicle enhanced with potentially commercial refueling. Involved Expendable Launch Vehicle, EELV, Heritage Super Heavy Vehicle enhanced with potentially commercial refueling. This discussion is contained in 2 sections of the chapter. Section 6.4 includes a comparison of the Ares 1 plus Ares 5 architecture with the Ares 5 Light dual launch architecture. Later, the Ares family and other options are contrasted in Section 6.5. How should crews be carried to low Earth orbit? U.S. government-provided systems, commercially provided systems with backup by U.S. government system. Section 6.4 contains integrated options that include both choices. 5. What is the most practical strategy for exploration beyond low Earth orbit? Moon first on the way to Mars with lunar surface exploration focused on developing capability for Mars. Flexible path to Mars via the inner solar system objects and locations, with no immediate plan for surface exploration, then followed by exploration of the lunar and/or Martian surface. Section 6.4 contains integrated options that have the moon first as their strategy, while Section 6.5 presents those that explore along the flexible path. The cross-case analysis of these options will be presented in Section 6.6. The committee addressed one other underlying question: what meaningful exploration program beyond low Earth orbit could be executed within the budget constraints represented in the FY 2010 budget. This will be the topic of Section 6.3. The committee considers the framing and answering of these questions individually and consistently to be its principal evaluation of the potential U.S. human spaceflight plans. The integrated options were prepared in order to understand the interactions of the decisions, particularly with regard to cost and schedule. By formulating the integrated options, the committee did not mean to constrain the possible final decision, but only to inform it. Other reasonable and consistent combinations of the choices are obviously possible, each with its own cost and schedule implications, and these could also be considered as alternatives. The integrated options evaluated are intended to represent the families of options, yet without presenting an unmanageable number of alternatives. The committee, in keeping with its charter, expresses no preference among these families, but does discuss the various advantages and disadvantages with respect to the evaluation criteria without weighing those attributes. 6.2.2 Integrated Options. The committee has defined 5 principal integrated options for human spaceflight. These have been selected from the more than 3,000 possible alternatives. Even after defining the choices for the 5 key decisions, 62 different options are possible. Not all of these combinations are worth considering. For example, it makes little sense to extend the shuttle life if the heavy lift will be based on EELV heritage. The 5 integrated options considered by the committee are: 1 baseline case, founded on the current constellation program, plus 4 alternate options, summarized for reference in Figure 6.2.2-1. The first 2 integrated options represent attempts by the committee to develop alternatives that are compatible with the FY 2010 budget profile. Each follows an approach that is principally aimed at lunar exploration. Option 1 uses the content of the program of record, while Option 2 extends the ISS, uses commercial crew delivery, skips development of the Ares 1, and uses Ares 5 Lite as the sole NASA launcher. See Figure 6.2.2-2. The baseline, Option 3, and the remaining 2 options are all fit to the same, less constrained budget profile. Options 3 and 4 are also lunar-oriented strategies. Option 3 is an implementable version of the program of record, with nearly exactly the content of the Constellation program, but with two minor changes in funding that the committee found necessary to extend the shuttle into FY 2011 and to deorbit the ISS in 2016. Option 4 again extends the ISS, light, and commercial crew. Option 5 is the one based on the flexible path. Integrated options 4 and 5 are explored in several variants that principally examine the sensitivity to the heavy launch systems. A more visual representation showing a possible design logic among these options is shown in Figure 6.2-3. 6.2.3 Methodology for Analyzing the Integrated Options. The committee used a synthesized cost-schedule-value methodology to assess the integrated options. In the first step, the committee created the integrated options that have been presented in Figure 6.2.2-1. These options were intended to link together representative combinations of the outcomes. The committee included the baseline case of the program of record in the mix. The other integrated options were chosen to allow some of the key trades, destination, launch vehicles, etc., to be contrasted. The committee used two candidate budget profiles for examining the integrated options. In the first, the guidance of the FY 2010 budget was enforced. This is called the constrained case, or simply FY 2010 budget case, as shown in Figure 6.2.3-1. It became apparent to the committee that options were needed that were not constrained to the FY 2010 budget. For planning and evaluation purposes, the committee created a second budget profile that rose from the FY 2010 budget number to a sum of $3 billion higher in 2014, and then rose at an expected inflation rate of 2.4% thereafter. Figure 6.2.3-1. Thus, by combining the 5 key decisions and the 2 budgetary scenarios, the committee produced the 5 integrated options with variants that are listed in Figure 6.2.2-1. To assess the benefits and risks of these integrated options, the committee next applied the evaluation criteria that had been selected, Section 6.1. In order to assess cost and schedule implications, the committee then examined the integrated options using the affordability analysis tool. The committee created a set of assumptions and ground rules for this analysis. These included budget profiles for the constrained and less constrained budgets and input manifests for each option. The costs used by the committee are intended to show the full cost of a program and do not take into account any potential contribution by international partners. Much of the cost data input into the analysis originated from the Constellation program. In these cases where the program cost estimates already contain a credit for an international contribution, this credit was removed by the committee in order to show the full cost. In other cases, the committee itself or other sources help to define the input. For example, the EELV Super Heavy Launcher costs were based on Aerospace Corporation examination of the EELV development plans. The organizational transition costs in Option 5B were provided by NASA headquarters. The in-space habitat in Options 5 was the result of an assessment of comparables performed by Aerospace. The committee provided estimates for the commercial crew to low Earth orbit costs, as discussed in Section 5.3.3. The aerospace team conducted the affordability analysis using the progress described in Figure 6.2.3-2. This analysis outputs key dates and element costs at the 65% confidence level. It also estimates the uncertainty on dates and costs. Output manifests are derived based on the 65th percentile confidence level and are illustrative of the pace of missions and elements utilized. The affordability analysis corrects the input cost in several ways. First, it estimates a range of expected growth on the cost for each program element from system design review SDR, start of Phase B, to completion, based on historical data of NASA programs. At the average, this introduces a 51% growth from the estimate held at SDR in the cost for development, DDT and E costs. For elements that have not reached their SDR, such as the Ares 5 or commercial crew service, this full correction was applied. For elements that have passed their SDR, credit was given for subsequent development and maturity of the design. For example, the mean cost of the Orion in the analysis due to this factor is only 25% higher than would be reported by the program of record at the mean. Other, more mature programs, such as the Ares 1, receive credit by a similar process. In operations, a 26% growth factor was applied to unproven systems, and no growth factor at the mean was applied to existing systems such as the shuttle or the ISS, or to defined budget items such as the technology program. NASA headquarters asked the program of record to report cost and schedule at the 65% level, and the committee attempted to report in a consistent manner. Note that on average, the difference between the mean of expected costs and the 65% confidence costs adds about 10% to all program costs calculated. Finally, the affordability analysis combines the development schedule of all the elements of the program. This process accounts for the additional cost of one element if another element it depends upon slips in the schedule. This integration of elements typically adds about an additional 10% to the total program costs, higher in more constrained budgets and lower in less constrained budgets. The committee then examined the outputs of the affordability analysis, and it made interpretations to extract from them the primary information of interest, recognizing the inherent uncertainty in the analysis. The reporting by the committee attempts to focus on its interpretation of the key milestones and associated uncertainties, and the pace of events after the initial milestone. End of section 13. Recording by Linda Marie Nielsen, Vancouver, BC. Section number 14 of Seeking a Human Spaceflight Program worthy of a great nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Spaceflight Plans Committee. 6.2.4 Reference Cases of the Entirely Unconstrained Program of Record. Unconstrained Program of Record. As an example of the affordability methodology applied to an actual integrated scenario, the reference case of an implementable version of the current Constellation program of record, unconstrained by any budget whatsoever, was analyzed. This implementation version contains only two slight variations from the actual program instituted by the committee: the provision for the shuttle to be flown out in 2011 and additional funds for the deorbit of the ISS in 2016. After withdrawal of U.S. participation at the end of 2015. Note that the ISS is not extended to 2020 in this particular reference case. As assessed by the committee, this case delivers Ares 1 Orion in late 2016, achieves human lunar return by the early 2020s, and a human-tended lunar outpost a few years later. These are very close to the dates held internally by the Constellation program. However, the committee's analysis indicates that in order to achieve the milestones on that schedule, the implementable program of record requires, in real year dollars, stated at 65% confidence, about $145 billion over the period from 2010 to 2020, which is about $45 billion over the guidance of the President's FY 2010 budget through 2020, and about $17 billion more than what is provided in the less constrained budget. The expenditures reach $14 billion per year in FY 2016, about $2 billion above the less constrained budget, and $5 billion over the FY 2010 budget for that year. The expenditures reach over $16 billion per year at their peak in FY 2019, $3 billion above the less constrained budget, and $7 billion over the FY 2010 budget for that year. Thus, the program of record, as assessed by the Constellation program, and the unconstrained implementable version of the program of record, as assessed by the committee, deliver Ares 1 and Orion in the mid to late 2010s, and they both have human lunar return in the early 2020s. Neither provides for an extension of the ISS or a space technology program of significance. The committee's finding is that the totally unconstrained implementable version of the program of record would significantly exceed even the less constrained budget. Unconstrained program of record with the ISS extension. This case would be identical to the above version of the program of record, but with the extension of the ISS to 2020. Since the budget for this case is unconstrained, no milestones slip, but more funds must be added to the NASA budget to operate the ISS in the years between 2016 and 2020. In this reference case, the Ares 1 Orion again are delivered in late 2016. Human lunar return is accomplished by the early 2020s, and human-tended lunar outpost is developed a few years later, again close to the dates held internally by the Constellation program. The ISS is extended to 2020, but in order to achieve these milestones, this variant of the program of record requires, at a 65% confidence level and in real year dollars, about 159 billion over the period from 2010 to 2020, which is about 59 billion over the guidance of the president's FY 2010 budget through 2020 and about 31 billion more than provided in the less constrained budget. The expenditures reach 15 billion per year in FY 2016, about 3 billion above the less constrained budget and 6 billion over the FY 2010 budget for that year. The expenditures reach about 19 billion per year at their peak in FY 2019, 6 billion above the less constrained budget and 10 billion over the FY 2010 budget for that year. Furthermore, the technology budget is a small fraction of $1 billion each year. Although these two reference options represent the greatest continuity from the existing program of record, the committee did not include them in the integrated options because they greatly exceed the FY 2010 budget profile and because the committee does not consider them to be programmatically competitive with the integrated options discussed below. 6.3 Integrated options constrained to the FY 2010 budget. 6.3.1 Evaluation of integrated options 1 and 2. The committee was asked to provide two options that fit within the FY 2010 budget profile. That funding profile is shown in Figure 6.2.3-1. It is essentially flat or decreasing through 2014, then increases at 1.4% each year thereafter, which is slower than 2.4% inflation rate used by the committee. Option 1. Program of record as assessed by the committee, constrained to the FY 2010 budget. This option is the Constellation program of record with only 3 changes: providing funds for the shuttle into FY 2011, including sufficient funds to deorbit the ISS in 2016, and constraining the expenditures to the FY 2010 budget. Under this option, the shuttle retires in FY 2011, and until its retirement in 2015, international crew carriers are used to rotate U.S. crews to the ISS. When constrained to the FY 2010 budget profile, Ares 1 and Orion are not available until the latter years of the 2010s, after the ISS has been deorbited, as shown in Figure 6.3.1-1. Starting in the late 2010s, piloted flights in the Ares 1 and Orion could begin at a pace of several flights per year, but with no specific destination defined. The heavy lift Ares 5 is not available until the late 2020s, allowing only orbital flights to the moon. In addition, there are insufficient funds to develop the lunar lander and lunar surface system until well into the 2030s, if ever. See Figure 6.2.2-2. In short, this program operates within current FY 2010 budget constraints, but offers little or no apparent value. Option 2. The ISS and lunar exploration, constrained to FY 2010 budget. This option extends the ISS to 2020 and begins a program of lunar exploration using Ares 5 Lite in the dual launch mode. The option assumes shuttle fly out in FY 2011, and it includes a technology development program, a program to develop commercial crew services to low Earth orbit, and funds for enhanced utilization of the ISS. As shown in Figure 6.3.1-1, the shuttle retires in FY 2011, and international providers rotate crew to the ISS until U.S. commercial crew services become available in the mid to late 2010s. Those providers are used to rotate the ISS crew until the space station's retirement in 2020. This option does not deliver heavy lift capability with the Ares 5 Lite plus Orion until the late 2020s and does not have funds to develop the systems needed to land on or explore the moon. See Figure 6.2.2-2. The committee applied its evaluation criteria to assess integrated options 1 and 2 as shown in Figure 6.3.1-2. The analysis shows that option 2, the ISS and lunar exploration, outperforms or equals option 1 in all criteria. It has an equal but low exploration preparation rating and performs equally on science, knowledge, public engagement, schedule performance, mission safety challenge, and workforce impact criteria. Option 2 is more highly rated under several criteria. The technology investment provides a higher rating in technology. The extension of the ISS improves its ratings in human civilization because of the added microgravity human physiology experience gained above the ISS, and in global partnerships because of the continued engagement of the international partners. Use of the commercial crew produces higher scores for economic development and an improved score due to lower life cycle costs. The resulting stronger advocacy increases the rating for sustainability. 6.3.2 Examination of alternate budget guidance. The first two integrated options allows examination of the underlying question: what meaningful exploration program beyond low Earth orbit could be executed within the budget constraints represented in the FY 2010 budget? The committee concludes that two executable alternatives comply with FY 2010 funding guidance. Option 2 is scored on the evaluation criteria more highly than Option 1, which provides for neither the ISS extension nor technology development, but neither alternative provides for a viable exploration program. In the process of developing these options, the committee conducted a sensitivity analysis to determine whether any reasonable exploration program, example with different heavy lift vehicles or a different exploration destination, would fit within the FY 2010 budget guidance. The committee could find none. In addition, the committee tried to develop a variant of the flexible path that fit within the FY 2010 budget, and such a variant looked no more promising than Option 2, with the first missions beyond low Earth orbit in the late 2020s. This analysis led the committee to its finding that human exploration beyond low Earth orbit is not viable under the FY 2010 budget guideline. It would be possible to continue the ISS and a program of human activity in low Earth orbit within this budget guidance and to develop the technology for future exploration, but the budget limitation would delay meaningful exploration well into the 2020s or beyond. 6.4 Moon First Integrated Options fit to the less constrained budget. 6.4.1 Evaluation of Integrated Options 3 and 4. Option 3 and 4 and its variants pursue the Moon First exploration strategy, but are not constrained to the FY 2010 budget profile. Rather, they are fit to the less constrained planning budget that the committee developed. The budget profile shown in figure 6.2.3-1 increases to $3 billion above the FY 2010 guidance between FY 2011 and FY 2014, and then grows with inflation at an expected inflation rate of 2.4% per year. While it was formulating integrated options, the committee quickly realized that viable options could not be found within the constrained budget. It then examined potential increases in the budget that would enable a sustainable and executable human spaceflight program. By examining several different potential expenditure profiles, the committee arrived at the above investment level that would provide for the extension of the ISS, allowing progress towards exploration beyond low Earth orbit, and make an investment in technology. It provided a useful standard by way which various options could be compared in a meaningful way. Option 3. Baseline Case. Implementable Program of Record. This is an executable version of the program of record. See figure 6.2.2-2. It consists of the content and sequence of that program, deorbiting the ISS in 2016, developing Orion, Ares 1, and Ares 5, and beginning exploration of the Moon. The committee made only 2 additions it felt essential: budgeting for the flyout of the shuttle in 2011 and including additional funds for the ISS deorbit. The committee then applied the less constrained budget profile. The committee's assessment of the schedule outcome for this option is shown in figure 6.4.1-1. Under that schedule, the shuttle retires in FY 2011, and International Cruise Services ferry U.S. crews to the ISS until its retirement in 2015. The option delivers the Ares 1 Orion in the mid to late 2010s and flights to low Earth orbit, but with no specific destination as yet definable. The Ares 5 becomes available, and human lunar return occurs in the mid-2020s, with a pace of about 2 flights per year. A lunar base begins to function about 3 years later. Although not included by the committee as an integrated option, a variant of option 3 is possible that extends the ISS to 2020, adds the technology program, and maintains all of the other content of option 3. Some would agree that this variant is actually the reference program on which NASA is embarked, but it should be emphasized that so far, no funds have specifically been allocated for continuing the ISS after 2015. Constellation Program, in its planning, assumed that funds that had been previously used for the operation of the ISS would become available to the constellation by 2016. Additionally, no funds were explicitly in the NASA plans for a robust, broad-based technology development program. The impact of extending the ISS to 2020 is to require the additional expenditure of about $14 billion between 2015 and 2020. The additional expenditure plus the technology program combined with developing the Ares 1 and Orion within the less constrained budget, causes significant slips to subsequent milestones. Orion Ares 1 do not become available until the late 2010s, serving the last few years of the ISS. The development of heavy lift and its use in human lunar return slips to the late 2020s, so that the Ares and Orion are left to either not fly at all for the better part of a decade or fly in that interval in Earth orbit without the ISS as a destination. The committee observed that the other options would be rated more highly by the evaluation process, so the committee did not pursue this variant of option 3. Option 4, Moon First. This option preserves the moon as the first destination for human exploration beyond low Earth orbit. It also extends the ISS to 2020, funds technology advancement, uses commercial vehicles to carry crew to the low Earth orbit, and funds the Space Shuttle into FY 2011. There are two significantly different variants to this option. See Figure 6.2.2-2. Variant 4A is the Ares 5 light variant. As shown in Figure 6.4.1-1, this option retires the shuttle in FY 2011 and relies on international launch support for crew delivery until the U.S. commercial crew services become available in the mid to late 2010s. The commercial crew provider ferries crew to the ISS until its retirement in 2020, after which there is a gap in human flight activity until the Ares 5 light in the dual launch mode is available for lunar exploration in the mid-2020s. The beginnings of a lunar base follow about 3 or 4 years later. Variant 4B, the shuttle extension variant. This variant includes the only foreseeable way to close the gap in U.S. human launch capability. As shown in Figure 6.4.1-1, this variant extends the shuttle to 2015 at a minimum safe flight rate. Shortly after the shuttle is retired, commercial service picks up the ferrying of crew to the ISS until its retirement in 2020. This variant also takes advantage of synergy with the shuttle by developing the more directly shuttle-derived heavy lift vehicle. However, even with the less constrained budget, the more directly shuttle-derived heavy launcher is not available until the middle of the 2020s, 10 years after the shuttle retires. Therefore, the problem of continuality of systems and workforce skills are diminished in the early years, but reappear later. The more directly shuttle-derived system has a higher recurring cost, so the flight rate within the less constrained budget drops below 2 crew flights per year to the moon, and a lunar base slips beyond 2030. Again, the committee applied its valuation process to these integrated options and variants that fit within the less constrained budget and follow a moon first strategy. The options can be compared in 2 steps. Figure 6.4.1-2 shows the comparison between option 3, the baseline, and options 4A, the Ares 5 light dual launch variant of the moon first architecture. This shows that option 4A matches or surpasses option 3 in all metrics considered. The sources of these differences are the use of the more capable Ares 5 light dual launcher coupled with the extension of the ISS, providing for more exploration preparation. The technology investment causes a higher score on the technology evaluation. The extension of the ISS improves the ratings on human civilization, more information on human long-term adaptation to space, and global partnerships. The availability of commercial crew launch gives an edge in life cycle costs and in economic expansion. Thus, the committee finds that even with the Ares 5 family launchers and the moon as a destination, there are ways potentially to extract more value from the program than to follow the baseline. In a second comparison, Figure 6.4.1 3 shows the relative valuation of the two variants of option 4, the moon first. Here the scores indicate some counts on which the Ares 5 Light variant 4A scores better than the shuttle-derived variant 4B. The use of the more capable Ares 5 Light dual launcher gives a higher score in exploration preparation. The use of the more economical Ares 5 Light gives a better evaluation in life cycle costs. The more capable Ares 5 Light dual launch allows simplification of launch and on-orbit operations, reducing mission safety risk. In contrast, the more directly shuttle-derived launcher in option B scores better in sustainability and workforce skills, both traceable to the continuation of the shuttle system and workforce. This decision trades a more capable vehicle for more short-term benefit from advocacy and smaller workforce impact with the shuttle-derived systems. End of section 14. Recording by Linda Marie Nielsen, Vancouver, BC. Section 15 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 6 Program Options and Evaluation, Part 3. 6.4.2 Examination of the Key Decision on the ISS Extension. Comparison of integrated options 3 and 4A allows examination of key decision concerning the future of the International Space Station. Should we stop U.S. participation in the ISS at the end of 2015 or continue U.S. participation through at least 2020, probably at an enhanced level of U.S. utilization? The background for this question was presented in Section 4.2. Extending the ISS would yield several benefits. Chief among these is the support for global partnerships. By ending participation in 2015, the U.S. would voluntarily relinquish its leading role in this phase of international space exploration. By extending the ISS, we would further develop the international partnerships upon which the ISS is based, encouraging these ties to evolve into long-lasting relationships for space exploration. The return on investment on the part of the U.S. would be enhanced by 10 years of well-funded utilization in the 2010s and by the operation of a national laboratory. The ISS extension issue couples with exploration preparation. If properly used, the ISS could be a more effective testbed for development of the technologies and systems for exploration. Extending the ISS also leads to improved evaluation in human civilization. The extra years on the ISS would allow a better understanding of the adaptation of humans to microgravity, and the extensions would produce more data for extremely long stays important in planning for exploration. The choice of ending U.S. participation in the ISS in 2015 really provides only one benefit, that of freeing up the roughly 2.5 to 3 billion per year needed to run the ISS, which can then be invested in the more rapid development of the exploration systems. The committee's integrated option analysis shows that if coupled to the choice of commercial crew launch system to low Earth orbit and the Ares 5 light heavy lift choice, this expenditure on the ISS would delay the exploration of the moon until the mid-2020s, only a few years after the most aggressive unconstrained profile would accomplish it. See section 6.2.4. By applying the evaluation criteria it developed, the committee finds extension of the ISS to 2020 to have greater value than the choice of ending U.S. participation in 2015. 6.4.3 Examination of the key decision on Ares 5 versus Ares 5 Lite dual launch. Unlike the other four key decisions, each of which has been reduced in this chapter to two main choices, the decision on heavy lift is more complex, as indicated in Figure 5.2-1. The decision can be represented by three successive choices. Figure 6.4.3-1. At the highest level, the nation faces a choice of basing the heavy lift capability on the NASA heritage systems, Apollo and Shuttle, or on the EELV heritage systems. Within the NASA heritage systems are those more directly based on the Shuttle and those that belong to the Ares family. Within the Ares family, there is the choice of Ares 1 plus Ares 5 system currently planned, or the Ares 5 Lite used in the dual mode for lunar missions as the only vehicle developed. The issues behind this set of decisions were discussed in section 5.2. In this section, the third choice will be examined. Because of the structure of the integrated options, the best head-to-head comparison of the other decisions is in the flexible path options in section 6.5. The committee considered the comparison of the Ares 5 Lite, which for lunar missions would be used in dual mode, with the current architecture of Ares 1 plus Ares 5. Setting aside the issues of crew launch on the Ares 1, which will be discussed in section 6.4.4, the principal distinguishing feature of the two alternatives is the extra heavy cargo launch capability that would be provided by the Ares 5 Lite dual launch during the lunar exploration. A secondary distinction is the relatively greater capacity of the Ares 5 compared with the relatively lower performance demands placed on the Ares 5 Lite. The main criteria involved in this comparison are exploration preparation, schedule, and program risks. The current baseline Ares 5 has more launch capability than the Saturn V, but current NASA studies show that when used in combination with Ares 1, it does not have enough launch capability to robustly deliver the currently planned landing and service systems to the moon. In order to deliver the greatest potential of the vehicle, many of the options to increase its performance have already been applied, including using 5.5 segment solid rocket boosters, SRBs, and 6 RS-68 family engines, both of which require further development. There is a concern expressed by some within NASA and by the committee that with performance already at the upper edge of what any Ares 5 family vehicle is likely to deliver, coupled with the potential weight growth of the payloads, the development will potentially face delays and added costs associated with weight reduction campaigns. In contrast, the Ares 5 Lite backs off on proposed performance by using a 5-segment SRB already in development and 5 RS-68 family engines. Thus, the development risk of the Ares 5 Lite is somewhat reduced. The essential difference between the two options is the use of 2 heavy lifters that for a lunar mission will give substantial margin and likely save development schedule and cost. The use of the 2 launch vehicles now decouples the operation of the Orion and Altair. The Ares 5 Lite dual launch allows a more robust Orion to be built, one that is capable of missions on its own. For example, launch with an Earth Departure Stage (EDS) to a near-Earth object (NEO), which will be discussed in section 6.5. Programmatically, the choice of the Ares 5 together with Ares 1 unquestionably has less impact on current workflow or contracts. However, the Ares 5 Lite preserves some of the investment already made for Ares 1 and would possibly allow some of the contract structure to stay in place. It would use the same 5-segment SRB as the Ares 1 and the same J2X engine for the Earth departure stage. It would deliver a heavy launch vehicle 3 to 5 years earlier than if the Ares 1 were built first, assuming the ISS is extended in both cases. Finally, construction of the Ares 5 Lite focuses NASA on the more challenging task of building the vehicle most needed for exploration, the heavy lift booster. The analysis performed for the committee indicated that the Ares 5 Lite dual launch scenario and the Ares 1 plus Ares 5 scenario would have comparable operating costs. In a normal year of lunar exploration, for example, in the mid-2020s, there would be 4 missions to the moon, 2 with crew and 2 with cargo. In the Ares 1 and Ares 5 architecture, this would require 2 Ares 1 launch vehicles and 4 Ares 5. In the Ares 5 Lite architecture, this same set of missions would require 6 Ares 5 Lites. Considering NASA's high fixed recurring costs, the difference in total cost between 4 and 6 launches a year of the same system would be a small fraction of the annual cost. In the Ares 1 and Ares 5 architecture, NASA would have 2 of the 6 launches by a less expensive vehicle, but would have to operate 2 launch systems with 2 processing flows at the Kennedy Space Center, offsetting potential savings. While the Ares 5 would nominally not have to be human-rated, the criticality of the payloads it would carry and the NASA development culture would likely and appropriately drive it to a nearly human-rated status. Ares 1 may have higher single-launch ascent safety than Ares 5. Both would be high-reliability rockets with the same capsule and launch escape system. The first stage of the Ares 1 is considerably simpler. However, because of the higher dynamic pressure in the flight profile of the Ares 1 and its solid rocket motor, a capsule on the Ares 1 would have a more challenging separation from the booster than a capsule of the Ares 5. Ares 1 is not planned to launch at a rate higher than 2 per year, raising questions about the sustainability of safe operations. In contrast, up to 6 Ares 5 lights are planned to launch each year, about the average rate of shuttle launches throughout the program's years of operation, contributing to a potentially higher demonstrated reliability. There is widespread confusion about the findings of the Columbia Accident Investigation Board, CAIB, on the issue of mixing crew and cargo. The CAIB report said, when cargo can be carried to the space station or other destinations by an expandable launch vehicle, it should be, page 211 of the CAIB report. That suggests that humans should not be put at risk to carry cargo as they are in the shuttle. The implication is not that humans should be launched along with cargo, if that makes sense, which was the case with Apollo. One of the two vehicle choices, the committee finds the Ares 5 light in the dual mode contributes to a higher score on the evaluation options than does the Ares 5. The critical difference is the use of the two Ares 5 family launchers for lunar missions. Even the Ares 1 were to be built. The committee's findings indicate that the exploration missions would benefit from the using the Ares 5 light in the dual mode as described. 6.4.4 Examination of the key decision on the provision of crew transport to low Earth orbit. The key question pertaining to crew launch to low Earth orbit is whether to carry the crews on systems provided by the U.S. government or on commercially provided systems with eventual operational backup by a U.S. government system. The Exploration Systems Architecture Study, ESAS, of 2005 developed a plan to launch crew to the ISS and to destinations beyond low Earth orbit using the Ares 1. As discussed in the background on this decision in section 5.3, this would be a launch system with very high ascent safety, would have high component commonality with the Ares 5, and would provide NASA organizationally with an opportunity to develop the Ares 1 before undertaking the more complex Ares 5. The alternative is to terminate the development of the Ares 1 and instead proceed with development of a commercial launch service to low Earth orbit for crew. If based on a high reliability rocket and with a capsule and launch escape system, this approach too could have high ascent safety. It would also have the potential for significantly lower development cost and therefore be available about a year sooner. Once operating, it would have the potential for significantly lower recurring costs, allowing the more rapid development of systems for exploration beyond low Earth orbit in a constrained resource environment. The development of commercial cruise service is not without significant programmatic risk, as discussed in section 5.3. The choice of Ares 1 as the crew launcher was probably a sound choice in 2005. As is often observed, the rocket equation has not changed. So any reason that NASA would come to a different solution for crew transport to low Earth orbit today than in 2005 would be due to changes in assumptions and constraints. The committee in fact concludes that many of the assumptions on which the Ares 1 crew decision was based have changed. In contrast, the committee found that the Orion should continue to be developed as a capable crew exploration vehicle, regardless of the decision on Ares 1. Likewise, it should be emphasized that the committee did not find any unsurmountable technical issues with Ares 1, With time and sufficient funds, NASA could develop, build, and fly the Ares 1 successfully. The question is, should it? First, from the perspective of schedule, the committee observes that because of technological delays and the shortage of funds, Ares 1 will not effectively service the ISS, since the launch vehicle is expected to come online in FY 2017 after retirement of the ISS. Even if the ISS is extended within constrained resources, the Ares 1 and Orion will not be available until near the end of the decade, serving during only the last few years of the ISS. As noted, safety is paramount. It is unquestionable that crews need access to low Earth orbit at significantly lower risk than the shuttle provides. The best architecture to assure such safe access would be the combination of a high reliability rocket and a capsule with launch escape system. While Ares 1 and Orion fit that description, so do other alternatives. The committee was unconvinced that enough is known about the potential failures of any of the prospective high reliability launchers, plus capsule and launch escape systems, to distinguish their safety in a meaningful way. The uncertainty in the safety models is large compared to the differences they predict among competing systems, and it is clear that many of the failure modes observed in practice are not captured in the safety analysis. The budgetary environment today is significantly more constrained than in the assumptions used for the ESAS. Despite the significant architectural commonality of the Ares 1 and Ares 5, the program now estimates that Ares 1 will cost $5 billion to $6 billion to develop, even assuming that all common costs are carried by the Ares 5. Within the existing budget constraints, that will delay the availability of the Ares 5 to the mid-2020s if the ISS is not extended, and another several years if the ISS is extended. When it begins operations, the Ares 1 and Orion would be a very expensive system for crew transport to low Earth orbit. Program estimates are that it would have a recurring cost of nearly $1 billion per flight, even with the fixed infrastructure costs being carried by Ares 5. The issue is that the Orion is a very capable vehicle for exploration, but it has far more capability than needed for a taxi to low Earth orbit. Another understanding that has changed since the ESAS was performed is the traffic model. Figure 6.4.4-1 indicates the number of operational flights of the Ares 1 based on the choices made in two other decisions, and based on projected flight rates and the schedules estimated for the less constrained budgets. There are no Gemini-style missions included in this count that simply orbit and do not service the ISS. In none of the combinations are there more than about 6 Ares 1 flights in the next decade, or a dozen in the next 2 decades. In the years since the ESAS, other conditions have changed as well. The NASA workforce has learned from the development of the Ares 1. With the approaching launch of the Ares 1X flight test vehicle, much of what will be learned may have already occurred. The sunk costs in Ares 1 will be partially recovered in the development of Ares 5 due to the commonality of the SRB J2X engine, etc. Further, a commercial space industry has continued to develop, in part due to the investment of NASA in the Commercial Orbital Transportation Services COTS program. Thus, the use of commercial vehicles to transport crews to low Earth orbit is much more of an option today than it might have been in 2005. Moving towards commercial crew services will also contribute to the evaluation on economic expansion, together with commercial launch services for cargo to the ISS and potentially in space refueling. The commercial crew options could further stimulate the development of a domestic competitive launch capability. Eventually, it could stimulate a commercial service for human transport to low Earth orbit that would be available to other markets. In summary, the committee found more potential contribution to the evaluation of integrated options due to the development of commercial crew service to low Earth orbit than in the continued development of the Ares 1. Unfortunately, neither option is without problems. The Ares 1 would be safe, but late to serve the ISS and expensive to operate. It would not be operated very often, or many times in total. It would delay by years NASA's start on a heavy lift launcher, although some of the development so far will be applicable to the Ares 5. Terminating Ares 1 would cause programmatic disruption. On the other hand, programmatic commitment at this time to commercial crew service to low Earth orbit has benefits and risks. It has the potential to be safe, sooner, and significantly less expensive. It would allow NASA to share operating costs with other customers while the domestic development capability is demonstrated. Some of the systems are largely notional. The committee finds that if this alternative is pursued, the backup of a human rateable heavy launcher should be accelerated, as discussed in Section 5.3. 6.4.5 Examination of the key question on shuttle extension. What should be the future of the Space Shuttle? A prudent fly out of remaining flights, currently part of NASA policy, but FY 2011 funding for it is not part of the President's budget, or an extension of the shuttle through 2015 at minimum flight rate. A third option discussed in Section 4.1 of extending the shuttle life by one flight is considered to be a variant of the 2011 flyout option, which should be resolved by NASA. The potential advantage of extending the shuttle through 2015 at a low but safe flight rate are to continue to support the ISS with heavy logistics, to smooth the short-term workforce dislocation of shuttle workforce, and to help preserve the critical workforce skills associated with launch operations. Extending the shuttle would also help close the gap by delaying the retirement of the only system the U.S. currently has, or is likely to have in the next 5 years, to deliver humans to low Earth orbit. When viewed in the integrated options, some of these potential advantages are conditional. Extending the shuttle in combination with developing the Ares 1 and Orion would not entirely close the U.S. crew launch gap. If the shuttle is retired in 2011, the Ares 1 plus Orion would become available in 2017, producing a gap of about 7 years. If the shuttle is extended within a fixed budget, the funds that would have paid for the development of the Ares 1 and Orion will be further limited, and that will delay their availability until late in the 2010s, producing a gap of at least several years at that time. Additionally, the infrastructure changes and workforce transition required for Ares 1 would be delayed. The gap is not closed, but shifts to the future. The only way to close the gap in U.S. crew launch is to commission a commercial service for transporting crew to low Earth orbit, which, because it is potentially less expensive to develop, may at some risk be available by 2016, even with extension of the shuttle. Other than this scenario, the committee found no way to close the gap. The inclusion in many integrated options of reliance on international crew launch services is an indication that the committee found this to be an acceptable alternative as an interim measure. Extending the shuttle would provide more up mass and down mass capability to the ISS in this interval, which would be a benefit. The current U.S. space transportation policy, dated January 6, 2005, prohibits the government from taking actions that would put it in competition with commercial providers in space transportation. There is already a contract for NASA to buy commercial cargo launches, and it is not the committee's intent that a possible shuttle extension disrupt plans for those commercial flights. Any additional shuttle flights would supplement the ability of the commercial carriers to service the ISS. The one integrated option that includes a shuttle extension specifically includes the full manifest of commercial cargo flights through 2015. Extension of the shuttle would require that the recertification done by NASA be verified to ensure it is consistent with the CAIB recommendation. Shuttle retirement is the current NASA plan, which is a position supported by the Aerospace Safety Advisory Panel. Extending the shuttle would have a beneficial impact on the near-term workforce issues. Some workforce reductions would be indicated by the reduced flight rate proposed, but there would be several years in which to manage these reductions. In 2015, when the shuttle finally retires, no NASA crew launch system would be available for several more years, and then the problem of maintaining key workforce skills would resurface. If, however, the commercial crew option were to be ready by 2016 or so, some national competence in crew launch would be nearly continuous. Technically, extending the shuttle makes the most sense if a directly shuttle-derived vehicle is chosen to replace the shuttle, which is the case in option 4B. The relative advantages of this option are discussed below in section 6.5.2. Taking all factors into consideration, the decision to extend the shuttle or not is a complex trade. Consideration of near-term access to low Earth orbit, workforce and skills issues supports the extension. These benefits primarily materialize if the shuttle extension is complemented by the development of commercial crew service to low Earth orbit. The potential life cycle costs and lower capability of the associated heavy launch system favor early retirement of the shuttle. End of section 15. Recording by Linda Marie Nielsen, Vancouver, BC. Section number 16 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 6, Program Options and Evaluation, Part 4. 6.5 Flexible path integrated options fit to the less constrained budget. 6.5.1 Evaluation of integrated option 5. In the final family of options are those that pursue exploration using the flexible path strategy discussed in section 3.5. Like the integrated options in section 6.4, these are not constrained to the FY 2010 budget profile. Rather, they are fit to the less constrained planning budget that the committee developed. As shown in figure 6.2.3-1, that budget profile increases to $3 billion above the FY 2010 guidance between FY 2011 and FY 2014, and then grows at a rate comparable to an expected inflation rate of 2.4% per year. Option 5, Flexible Path. This option follows the flexible path as an exploration strategy. It operates the shuttle into FY 2011, extends the ISS until 2020, and funds technology development. In all three variants, as shown in figure 6.5.1-1, the commercial transport service becomes available in the mid to late 2010s. To begin ferrying U.S. crew to the ISS. By the early 2020s, after the heavy lift vehicle is developed, development of a small in-space habitat and an in-space restartable propulsion stage follows. All three variants also include a hybrid lunar lander that is smaller than the Altair. See figure 6.2.2-2. The ascent stage is developed by NASA, but the descent stage is assumed to be commercially developed, building on the growing industrial capability pursuing NASA's Lunar Lander Challenge and the Google Lunar X Prize. The commercial lander could also use the NASA-developed in-space restartable engine that would be used for missions on the flexible path. There are three variants with this option. They differ only in the heavy lift vehicle. Variant 5A as the Ares 5 Light variant. It develops the Ares 5 Light, the most capable of the heavy lift vehicles in this family of options. Figure 6.5.1-1 shows the schedule for this option. The Ares 5 Light becomes available in the early 2020s, and the flexible path missions to the Moon, Earth escape to Lagrange points or near-Earth objects, and a Mars flyby occur at about 1-year intervals. Initial lunar landing takes place in the mid to late 2020s. Lunar buildup occurs at a rate of about 2 flights per year with the more capable Ares 5 Light. On-orbit refueling or the use of a second Ares 5 Light is necessary for the most energetic of the flexible path missions. Variant 5B employs an EELV Heritage Commercial Super Heavy Lift Launcher and assumes a different and significantly reduced role for NASA. It has an advantage of potentially lower operational costs, but requires significant restructuring of NASA. It follows the same timeline as Variant 5A up to the landing on the Moon. On-orbit refueling is used for the flexible path missions. Therefore, the EELV Heritage Super Heavy flies 2 missions of 3 launches per year to the Moon, but does not carry as much load on each mission unless on-orbit refueling is used. Thus, a slower lunar development or the development of a less massive lunar infrastructure results. Variant 5C uses a directly shuttle-derived heavy lift vehicle, taking maximum advantage of existing infrastructure, facilities, and production capabilities. It too follows about the same timeline up to the first lunar landing and uses on-orbit refueling for flexible path missions. When lunar missions begin, the higher recurring cost of the more directly shuttle-derived heavy launcher causes a slower rate of lunar buildup. Comparison of the three flexible path valuations is shown in Figure 6.5.1-2. The distinguishing features are the Ares 5 Light option 5A has an edge in exploration preparation due to the more capable vehicle and in mission safety challenge because the more capable vehicle requires less complex ground and on-orbit operations. The EELV Heritage Super Heavy Option 5B has an edge in technology because it includes a new US-developed large hydrocarbon engine and the lowest, i.e. best, life cycle costs due to the commercial nature of this operation. It does poorly in sustainability due to the disruption in contracts, workforce transitions, and the new way of doing business that would be necessary at NASA. The more directly shuttle-derived heavy launcher in option 5C has an edge in sustainability due to advocacy for shuttle-derived systems, but does poorly in life cycle costs. 6.5.2 Examination of the key questions on Ares 5 family versus shuttle-derived heavy launcher. In section 6.4.3, the decisions on heavy lift were outlined, and the comparison between the Ares 5 and Ares 5 Light was discussed. In this section, the comparison between the Ares 5 family and the more directly shuttle-derived launcher, as indicated by the decision tree of Figure 6.4.3-1, will be examined. The background for these decisions was presented in Section 5.2. As discussed in Section 6.4.3 above, the two Ares 5 family launchers under consideration are the Ares 5 with 5.5 segment SRBs and 6 RS-68 family engines, and the Ares 5 Light with 5 segment SRBs and 5 RS-68 family engines. In comparison with the directly shuttle-derived vehicles, these differences among the Ares 5 family are small. Also discussed in Section 5.2, the primary candidate for consideration from the more directly shuttle-derived family is the inline variant. This vehicle uses two 4-segment SRBs, some number of Space Shuttle main engines, SSMEs, or the engine's expendable derivative, the RS-2E, 3 or 4 typically, on the bottom of a re-engineered 8.3 meter diameter tank with an inline EDS and on top a cargo payload or human carrying capsule with a launch escape system. To the less trained eye, such a vehicle would look much like an Ares 5. In fact, at the end of the ESAS study in 2005, the candidate for the CALV cargo launch vehicle was exactly the shuttle-derived variant just described. In the 4 years since ESAS, the design has evolved into the Ares 5 known today. Thus, the considerations for this choice of a more directly shuttle-derived vehicle versus Ares 5 more or less exactly play out the trade studies conducted by NASA in the last 4 years. The principal difference between the two families in the use of the SSMEs or their expendable derivative on the more directly shuttle-derived launcher versus the use of the RS-68 family engines on the Ares 5 the use of more shuttle-derived components lowers the development costs somewhat and accelerates by about a year the availability of heavy lift. But these dates of first availability of heavy lift are in the early 2020s at best, due to budget constraints and likely extension of the ISS. Therefore, even if a shuttle-derived vehicle is developed and the shuttle is extended, there is about a decade of gap in heavy vehicle operations. This erodes the benefit of using the shuttle extension and a more directly shuttle-derived vehicle to close the critical workforce gap. Using the more directly shuttle-derived vehicles does produce a somewhat less capable vehicle, figures 5.2-2 and 5.2.1-1, and increases the recurring costs for a given mass launched to low Earth orbit. For example, in a year of planned constellation lunar operations in the mid-2020s, there would be 3 shuttle-derived vehicle launches for each mission to the moon, which would deliver a mass comparable to that of 2 Ares 5 class launchers. Cargo missions would use 1 or 2 shuttle-derived launchers, with 2 crew and 2 cargo missions per year. This would require 8 to 10 launches of the shuttle-derived launcher, each with 3 or 4 SSMEs or derivatives, for a total of 24 to 40 of the shuttle engines being used, with a resulting high recurring cost. Among the other notable differences between the Ares 5 family and the more directly shuttle-derived launcher family is the mission launch reliability. Since the latter requires 3 launches for each planned constellation lunar mission, there would be a somewhat lower reliability in any given time window than would be provided by the Ares 5, which only would require 2 launches in the same time window. The committee considered as an issue the commonality with the National Space Industrial Base. The Ares 5 uses engines from the RS-68 family, with commonality in the industrial base with those used on the EELVs by National Security Space. Both the Ares 5 and the more directly shuttle-derived vehicle have commonality in the solid rocket motors with vehicles used in national security space. In summary, the committee viewed the decision between the Ares 5 family and the shuttle-derived family as one driven by cost and capability. The development cost of the more shuttle-derived system would be lower, but it would be less capable than the Ares 5 family and have higher reoccurring costs. There are potential workforce and skill advantages associated with the use of the more directly shuttle-derived system, but the long gap between when the shuttle is retired in 2011 or even 2015 and when the shuttle-derived heavy launcher becomes available in the early to mid-2020s would diminish the potential value of the workforce continuity associated with shuttle derivatives. 6.5.3 Examination of the key question on NASA heritage versus EELV heritage super heavy vehicles. The highest level decision on heavy lift launch vehicles is whether to base the launch system for exploration on these NASA heritage vehicles or on the further extensions of the EELV heritage vehicles up to the 75 MT range, figure 6.4.2-1. It should be emphasized that this is not the existing EELV heavy launcher, which has a maximum payload to low Earth orbit of about 25 MT, but rather requires the development of a substantially new vehicle, in part of existing components and manufacturing facilities. The EELV Heritage Super Heavy Launch Vehicle would be capable of launching about 75 MT to low Earth orbit, significantly less than the Ares 5 family at 140 to 160 MT, or the shuttle-derived vehicle in the range of 100 to 110 MT. However, the EELV Heritage Super Heavy is still larger than the committee's estimated smallest possible launcher to support exploration, which is in the range of 40 to 60 MT. In a nominal piloted lunar mission without in-space refueling, the EELV Heritage Super Heavy would require 3 flights, potentially with an additional crew taxi flight, versus 2 launches for the Ares 5 Lite. In the flexible path options, the EELV would not require more launches, but would involve more on-orbit operations than Ares 5 family approach. For these launch rates, the EELV would have a lower recurring cost than the NASA Heritage vehicles. Initially, the EELV Heritage Super Heavy vehicle would use the Russian RD-180 hydrocarbon-fueled engine currently used on the Atlas V. In the cost analysis utilized by the committee, provision was made for the development of a new large domestic engine to replace the RD-180 for both NASA and national security missions. This would have technology benefits and would provide value to national security systems. While there are technical differences between the two families, the committee intended the principal difference to be programmatic. The EELV Heritage Super Heavy would represent a new way of doing business for NASA, which would have the benefit of potentially lowering development and operational costs. The committee used the EELV Heritage Super Heavy vehicle to investigate the possibility of an essentially commercial acquisition of the required heavy launch capability by a small NASA organization similar to a system program office in the Department of Defense. It would eliminate somewhat the historic carrying cost of many Apollo and Shuttle era facilities and systems, thus creates the possibility of substantially reduced operating costs, which may ultimately allow NASA to escape its conundrum of not having sufficient resources to both operate existing systems and build a new one. However, this efficiency of operations would require significant near-term realignment of NASA, substantial reductions in workforce, facility closures, and mothballing would be required. When the committee asked NASA to assist the cost of this process, the estimates ranged from $3 billion to $11 billion over 5 years. Because of these realignment costs, the EELV Heritage Super Heavy does not become available significantly sooner than the Ares 5 or shuttle-derived family of launchers. The transition to this way of doing business would come at the cost of cutting deeply into the internal NASA capability to develop and operate launchers, both in terms of skills and facilities. There would be other consequences at the national level. Needless to say, the co-development of the EELV Heritage Super Heavy would require careful coordination between NASA and the Department of Defense to ensure joint value. In summary, the committee considers the EELV Heritage Super Heavy vehicle to be a way to significantly reduce the operating cost of the heavy lifter to NASA. In the long run, it would be a less capable vehicle, but probably sufficiently capable for the mission. Reaping the long-term cost benefits would require substantial disruption in NASA and force the agency to adopt a new way of doing business. The choice between NASA and EELV heritage is driven by potentially lower development and operations costs, favoring the EELV heritage system, versus continuity of the NASA's system design, development, and mission assurance knowledge and experience, which would provide higher probability of success and predictable developments favoring NASA systems. EELV heritage launch systems, due to their lower payload performance, would require significantly greater launch and mission complexity to achieve the same total mass in orbit. The EELV option would also entail substantial reductions in the NASA workforce and closure of facilities necessary to obtain the expected cost reductions. 6.6 Comparisons across integrated options. 6.6.1 Cross-option comparisons. A cross-family comparative evaluation is shown in Figure 6.6.1-1, which contrasts the baseline, option 3, with the Ares 5 Lite variant of the flexible path, option 5A. The flexible path option scores more highly than the baseline on 9 of the 12 criteria. The higher rankings include exploration preparation due to much more capable launch systems, technology due to investment in technology, science because of more places visited, human civilization due to the ISS extension, economic expansion because of commercial involvement in space elements and crew transport, global partnerships gained by extending the ISS, public engagement by visiting more new locations and doing so each year, schedule, exploring beyond low Earth orbit sooner, life cycle costs due to commercial crew services. 6.6.2 Examination of the key question on exploration strategy. The fifth and final of the key questions guiding the decisions on the future of human spaceflight is: what is the most practical strategy for exploration beyond low Earth orbit? In Chapter 3, 3 exploration strategies were presented, but the choice of exploration of Mars first was found not to be viable at this time. The 2 remaining choices are Moon first on the way to Mars, with surface exploration focused on developing capability for Mars, flexible path to Mars via the inner solar system objects and locations, with no immediate plan for surface exploration, then followed by explorations of the lunar and or Martian surface. This contrast can be highlighted by comparison of the reference variant for Moon first option 4A and flexible path option 5A, as shown in Figure 6.6.2-1. These 2 options differ only in exploration strategy. The flexible path equals or exceeds the ratings of the Moon first option in all areas. It has an advantage in science, economic expansion, public engagement, and schedule. These front distinctions will be examined below. From the perspective of science knowledge, the Moon first approach would allow better understanding of the evolution of the Moon and the Moon's surface as a record of events in the evolution of the solar system. The flexible path would explore near-Earth objects and also demonstrate the ability to service science observatories at the Lagrange points. The crews on such missions would potentially interact with robotic probes on the surface of Mars, returning samples as well. In some of its alternatives, including the one costed in Section 6.5, the flexible path also allows exploration of the Moon, though at a more limited scale than in the Moon First approach. Considering that we have visited and obtained samples from the Moon, but not near Earth objects or Mars, and also that the flexible path develops the ability to service space observatories, the science knowledge criterion slightly favors the flexible path. Broadly, the more complex the environment, the more astronaut explorers are favored over robotic exploration. In practice, this means the astronauts will offer their greatest value added in the exploration of the surface of Mars. It is likely that the flexible path approach would engender more public engagement than the Moon First approach. In every flight, the flexible path voyages would visit places where humans have never been before, with each mission extending farther than the previous one, potentially heading to a full dress rehearsal for a Mars landing. A potential liability of the Moon First option is that it could appear to some stakeholders as a modern repetition of exploration that was accomplished 50 years earlier. Schedule also favors the flexible path scenario. The fundamental economics of the investment by NASA to begin flights on the flexible path and Moon First options are shown in Figure 6.6.2-2. Before lunar exploration can begin, NASA must complete 4 development programs: the Heavy Lift Launcher, the Orion capsule, the Altair lander, and at least some of the lunar surface systems. Even the well-funded Apollo program only had to complete the first 3 of these. In contrast, exploration on the flexible path could begin with just the capsule and launcher, and then slowly develop much less costly in-space propulsion stages and habitats. After NASA explores on the flexible path for a half decade or so, it could then invest in the lunar lander and surface systems. In summary, the flexible path provides for exploration beyond low Earth orbit several years earlier and allows a less demanding programmatic investment profile. Because the flexible path option contained a commercially developed lunar lander descent stage, it was evaluated more highly in economic expansion as well. The use of a commercial lander is not fundamental to the execution of the flexible path, but is more likely in this strategy. The lunar landing would be later, involve a simpler lander, and follow the development by NASA of the in-space restartable engine, of which would make a commercial system more viable in the flexible path than in the Moon First strategy. On the evaluation criteria on which the two strategies score equally, there are some distinctions. Under human civilization, both lead to better understanding of human adaptation to space, but the flexible path aids in the protection of Earth from near-Earth objects. From the viewpoint of mission safety challenges, the two strategies are also about equal. Operations at the Moon are closer and allow return to Earth more rapidly, but landing on and launching from a surface is a dynamic environment. In contrast, the flexible path missions are less dynamic, but occur farther from Earth. There is no reason to believe that the remaining evaluation criteria favor one or the other strategy for exploration. They have more to do with how the strategy is implemented. For example, either the moon first or flexible path could be the basis for a new or extended international partnerships in space. In summary, 8 of the 12 criteria favor neither the moon first nor flexible path strategies for exploration. However, of the 4 that do discriminate, science knowledge, public engagement, schedule, and life cycle costs all slightly to moderately favor the flexible path. Finding on evaluation of program options. Options for human spaceflight should be evaluated by a set of criteria that are consistent with goals. The committee identified 12 criteria which measured the capability of an option to satisfy its stakeholders along the motivations listed above, along with programmatic issues of safety, cost, schedule, sustainability, and workforce impact. It is the role of decision makers to prioritize these measures. Findings on options for the human spaceflight program. The committee developed 5 alternatives for the human spaceflight program. In reviewing these, it found human exploration beyond low Earth orbit is not viable under the FY 2010 budget guideline. Meaningful human exploration is possible under a less constrained budget, ramping up to approximately $3 billion per year in real purchasing power above the FY 2010 guidance in total resources. Funding at the increased level would allow either an exploration program to explore the moon first, or one that follows a flexible path of exploration. Either could produce results in a reasonable time frame. End of section 16. Recording by Linda Marie Nielsen, Vancouver, BC.
Section 17 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Section 17. Chapter 7. Critical Technologies for Sustainable Exploration. The Space Act of 1958 calls on NASA to preserve the U.S. position as a leader in space technology. Today, the alternatives available for exploration systems are severely limited because of the lack of a strategic investment in technology development in past decades. Looking forward, NASA has before it an unprecedented opportunity to make an effective strategic technology plan. With a 20-year roadmap of exploration laid before it, NASA can make wise technology investments that will enable new approaches to exploration. 2 recent reports of the National Academies have made recommendations in this regard. The investment should be designed to increase the capabilities and reduce the costs of future exploration. NASA has conducted studies to demonstrate the mass reduction and therefore operational cost savings that are achievable with investments in technology. Figure 7.1-1. With technology investments, the mass required for a Mars exploration mission decreases from 8 times the mass of the International Space Station to a mass comparable to the station. Notes: results are cumulative and thus trends will be different for different technology combinations and sequences. The change between points shows the relative mass savings for that particular technology. 2018 one-year round-trip mission, crew of 4, lander pre-deployed. All propulsion chemical, aero capture, advanced propulsion, closed-loop life support, advanced materials, maintenance and spares, advanced avionics. As an illustration, it indicates an almost tenfold reduction in mass required for future missions to Mars. If appropriately funded, a technology development program would re-engage the minds at American universities, in industry, and within NASA. This will benefit human and robotic exploration, the commercial space community, and other U.S. government users alike. 7.1. Fundamental unknowns. 3 factors affecting long-duration human space exploration are of central importance, yet do not lend themselves to definitive assessment based on the available data. 1. The effects of prolonged exposure to solar and galactic cosmic rays on the human body. 2. The impact on humans of prolonged periods of weightlessness, followed by a sudden need to function without assistance in a relatively strong gravitational field. And 3. The psychological effects on individuals facing demanding tasks in extreme isolation for well over a year with no possibility for direct outside human intervention. While the specific technologies to address needed capabilities can and will be debated, if the United States wishes to conduct more and more capable missions in the future with near constant budgets, it is essential to develop and bring to flight readiness the technologies required. This will not happen without a sustained plan in which needed capabilities are identified, multiple competing technologies to provide that capability funded, and the most mature of them demonstrated in flight so that exploration architectures can then depend on them. For many technologies, it is less expensive to design a flight demonstration using the facilities on the International Space Station than it would be to design a free-flying mission for each and every technology demonstration. Radiation effects on humans. Beyond the shielding influence of the Earth's magnetic field and atmosphere, ionized atoms that have been accelerated to extremely high speeds in interstellar space fill the solar system. The effects of such galactic cosmic radiation on crews on long-duration spaceflight far from the Earth are a significant concern. Additionally, normal solar flare activity also occasionally releases radiation potentially injurious to humans. On the Moon or on the surface of Mars, techniques are available to shield a human habitat from these sources of radiation, but the massive shielding is cost-prohibitive for a spacecraft. These radiation effects are insufficiently understood and remain a major physiological and engineering uncertainty in any human exploration program beyond low Earth orbit. A 2008 report by the National Research Council concluded, quote, "Lack of knowledge about the biological effects of and responses to space radiation is the single most important factor limiting the prediction of radiation risk associated with human space exploration," unquote. A robust research program in radiobiology is essential for human exploration. Research on these radiation effects on humans is limited on the International Space Station since it is partly shielded by the Earth's magnetic field. In addition to studying the effects of galactic cosmic radiation, GCR, there are mitigation strategies such as more effective shielding techniques or the use of high shielding mass on a reusable habitat that cycles between Earth and Mars without being accelerated for each mission, cycler habitat, that need additional study. Micro and hypergravity effects on humans. While significant data on crew adaptation to microgravity now exists from extended International Space Station stays, there is a need to further develop countermeasures and build an understanding of even longer profiles that will be encountered in exploration beyond low Earth orbit. The International Space Station is a logical place to conduct such research, and the United States should obtain these data before the International Space Station is retired. Psychological effects of extreme isolation on humans. While many experiments have been conducted on Earth to examine the effects of prolonged isolation on humans needing to continue to function at a high level, these experiments generally fall short of simulating the circumstance of extreme physical confinement in which the participant realizes there is no opportunity to end the experiment. In this regard, missions to Mars would be far more demanding than those to the Moon. Mars, at its closest, is 56 million kilometers from the Earth, or whereas the Moon is 380,000 kilometers. In the latter case, return is generally possible within a few days. In contrast, Martian circumstances may require many months or years for an emergency return to Earth. 7.2 Propellant Storage and Transfer in Space. Wernher von Braun wrote of the significant benefits to be gained from propellant transfer and storage in space. Up to this time, the normal approach for inserting payloads on trajectories away from low Earth orbit towards the Moon or Mars is to use an upper stage called an Earth Departure Stage, EDS. In the conventional scheme, the Earth departure stage burns some of its fuel on the way to orbit and arrives at low Earth orbit partially full. The remainder of the fuel is expended, injecting the payload towards its destination beyond low Earth orbit. An alternative discussed in Chapter 5 is to refuel in space so that the EDS can arrive in orbit mostly empty and be refilled. After leaving Earth, exploration systems will still need to make 1, 2, or 3 propulsive maneuvers, often after months in space. Again, past experience is to use storable propellants for these maneuvers, but in human exploration, the cost of doing this becomes large. The benefit of in-space cryogenic transfer and storage is that it enables refueling in space and the use of high-energy fuels for in-space propulsion. Using propellant transfer for the EDS, for example, allows more mass to be injected from the Earth with a given launch vehicle or a smaller launcher for a given payload. Today, these technologies are considered ready for flight demonstration according to both NASA and industry experts working in the field. Figure 7.2-1. Nonetheless, legitimate questions remain as to the practical feasibility of the approach. These concerns generally center on cryogenic transfer and storage technology. Cryogenic transfer, storage, and gauging in a microgravity environment create challenges that have been investigated by researchers in the laboratory for decades. Automated rendezvous and docking of delivery tankers has recently been demonstrated. Capabilities that remain to be demonstrated include long-term storage of very cold cryogenic propellant without excessive boil-off, transferring cryogenic propellant between tanks in a zero-G environment, making cryogenic fluid line connections, gauging the quantity of propellant in the tanks in a zero-G environment. Figure 7.2-2 shows the maturity of various technologies based on the NASA Technology Readiness Level (TRL) system, summarizing the current assessment of capabilities required for propellant transfer and storage on orbit. Figure 7.2.2 Technology Readiness of Components for In-Space Refueling. Source: Review of U.S. Human Spaceflight Plans Committee. Technology: Most mature approach. Status: Liquid acquisition, surface tension device plus setting, ground demonstrations, needs flight test. Propellant gauging, capacitance probe plus settling, mature technology with settling. Ullage gas management, settled vent, mature technology with settling. Transfer line conditioning, recirculation, mature technology with settling. Automated fluid coupling, extension of probe used for propellant couplings on orbital express. Flight demonstrated with storables. Needs flight test with cryogens. Insulation and thermal management. MLI is mature technology. Vapor-cooled shield further lowers boil-off. Ground demonstrations needs flight test. These cryogenic technologies have reached the point where a flight demonstration is the next logical step in development before this capability can begin to be designed into systems. The two technologies of liquid acquisition, collecting fluid in microgravity near the point from which it will be withdrawn from a tank, and automated fluid coupling cannot be tested in a realistic environment without in-space demonstration. Cryogenic coolers are needed for true zero-boil indefinite storage of liquid hydrogen, LH2, but other technologies listed in the table are intended to negate this problem for storage up to 1 year. 7.3. In situ propellant production and transport. After mastering the technologies for storing and transferring propellant in space, the next step is to manufacture propellant from resources already there. The lunar surface and some near-Earth objects are the only known sources of suitable resources that can be brought feasibly to cislunar space, such as to the Earth-Moon Lagrange point L1, which was identified as a promising candidate for a cislunar propellant depot in a 2004 NASA study. In situ propellant production requires the combination of two unique capabilities: 1. Producing the propellant, and 2. Transporting it economically. Oxygen is abundant in all lunar rocks and regolith, dirt without organic material, and a variety of chemical processes to extract it have been demonstrated in Earth-based laboratories. These propellant production methods must next be demonstrated on the lunar surface through robotic missions. Collecting lunar material and bringing it to a lunar-based processing station presents a great challenge. Laboratory work has shown that this will likely require both robotic and human-tended missions to mature the technology. In addition, it is also extremely important to produce hydrogen for fuel in space. If hydrogen can be economically extracted from the Moon, it will likely serve as a source of propellant for future exploration missions. If it cannot be produced, the case for exporting propellant from the Moon becomes less compelling, and near-Earth objects would rise in importance. Discoveries in recent years do suggest the availability of significant hydrogen deposits at the lunar poles. In addition, Apollo samples showed useful hydrogen deposits from the solar wind implanted in the regolith. These regolith deposits would require processing large amounts of material comparable to coal extraction on Earth. Robotic exploration of the Moon continues today, and further interesting sources of resources may well be found. The composition of near-Earth objects is less well understood than the composition of the Moon because of the current dependence on telescope-based observations and inferences drawn from meteorites reaching Earth. These data suggest that almost any desirable resource can be found on near-Earth objects. But since each near-Earth object is a distinct body with its own orbit and properties, it is difficult to make generalizations about how resources would be extracted and returned to cislunar space. It is worth noting that in some cases, the energy required to return mass from a near-Earth object to near-Earth space is significantly less than to return mass from the lunar surface to Earth-Moon L1 Lagrange point. Therefore, further robotic exploration and human-tended pilot visits to near-Earth objects are particularly interesting subjects for future exploration. Reusable chemical rockets might also be used to deliver in situ propellant from the Moon to the Earth-Moon L1 Lagrange point. Space tugs carrying and using hydrogen are generally more compelling than tugs carrying and using other propellants. As an alternative, because of the Moon's low gravity, non-chemical propulsion should also be considered. Catapults, tethers, and beamed energy are likely to become practicable for lunar to L1 transport long before they become practicable for Earth to orbit launch, and should continue to be investigated. Nonetheless, their application appears to be far off. Because about 2/3 of the mass on an Earth to Mars to Earth mission would be propellant, cost-effective lunar-produced propellant could decrease the mass that must be lifted from Earth by a factor of 2 to 3. Further, achieving industrial levels of oxygen and hydrogen production on Mars would greatly simplify the challenge of transporting fuel for the return trip from Mars to Earth. In situ propellant produced on Mars has been considered as well. Oxygen could be extracted from the carbon dioxide-based Martian atmosphere, and both oxygen and hydrogen could be extracted from Mars' ample ice. Although laboratory work for extracting resources from Mars is promising, the technology remains to be demonstrated under realistic circumstances. 7.4. Mars orbit to surface transportation. The entry, descent, and landing of cargo on Mars is difficult because Mars has sufficient atmosphere to drive the design of landing systems, but inadequate atmosphere for feasible parachutes or wings to safely land astronauts on the surface. Scientific probes landing on Mars have used a complex mix of aerodynamic braking and rocket propulsion. These techniques will have to be improved before larger robotic or crewed missions can be sent to Mars. This research and technology development program needs to be started soon because it will require many iterations and increasingly larger missions before NASA is ready to demonstrate a safe, crewed Mars landing. Meanwhile, the intermediate results would greatly benefit future robotic missions. Because of the unique landing challenges posed by Mars, a robust human presence will require an advanced Mars orbit to Mars transportation system, most likely a reusable system that could transport cargo and people between the Martian surface and a depot located nearby. Nuclear thermal rockets using in situ Martian-produced propellant would fly to Martian orbit, collect a payload, and then use aerodynamic braking for the initial descent, followed by nuclear rocketry to land. Alternately, a chemical rocket would need to refuel on both Mars and in near-Mars space, such as on the Martian moon Phobos. Use of Phobos for propellant production would benefit transportation both to and from the Martian surface and provide the propellant for astronauts to return from Mars to Earth. A Phobos-based teleoperated exploration of the Martian surface, returning with samples from that surface, would likely precede a crewed Mars landing mission and would provide dramatically more responsive remote control than with the communication delays incurred between Mars and Earth. The use of Phobos and/or Mars-produced in situ propellant would likely reduce the flight cost of a crewed Mars landing expedition by a factor of 2 to 3. 7.5. Advanced space propulsion. Since the 1950s, advanced space propulsion has been recognized as an extremely desirable technology for Mars missions, as is the possibility of aero capture. See Figure 7.1-1. The application of advanced space propulsion to crewed missions could significantly reduce the amount of propellant used, while providing sufficient thrust to build up interplanetary velocities relatively quickly, over days or weeks instead of months or years. Unfortunately, the physics of the problem are such that the more a vehicle tries to minimize propellant usage, the more power it consumes. Yet, since the power supply weight increases with power generation requirements, a more substantial power supply can negate some or all of the benefits of lower propellant usage. Two promising advanced space propulsion technologies are based on solar and nuclear energy sources. Solar. Current solar power collectors are too heavy to deliver dramatic benefits in space propulsion. Solar electric thrust is used today for some satellites, and it may play a role in cargo transportation from LEO to, for example, L1 and back. Unfortunately, the acceleration it provides is so low that it would take months or years to get from Earth to the Moon, for example. As a result, for solar-powered advanced propulsion to provide revolutionary benefits, either far lighter, thin-film solar arrays must be matured, or the heavy solar power collector must be left off the spaceship and the power from the collector beamed by lasers to lightweight collectors aboard the ship. Theoretical studies indicate this latter technology is physically plausible, but it hasn't made it out of the laboratory. In addition, the beam can only be held together over distances up to a few 100,000 kilometers with a reasonable-sized transmitter. Solar technology requires research and development and flight demonstrations, as well as a large investment to build the solar power collector and beam transmitter in space. However, such an effort might pave the way for transmission of power to the Earth for domestic use, although it is not known whether such systems will prove economical even if they were to be technically feasible. Nuclear. A more mature technology, nuclear thermal propulsion, reached advanced ground firing demonstrations during the 1960s before the program was canceled. With nuclear thermal propulsion, a nuclear reactor heats hydrogen and then ejects it to provide thrust. A nuclear electric thruster, on the other hand, produces electricity to run an electric thruster, such as high-power Hall effect thrusters or the Variable Specific Impulse Magnoplasma Rocket (VASIMR) thruster NASA is currently funding. Nuclear reactors today provide a substantial fraction of U.S. electricity production, and other countries use nuclear reactors to produce an even larger fraction of their domestic power. For advanced space transportation, much lighter nuclear reactors are required. Although expensive to develop, this solution could cut the cost of missions from Earth by a factor of 2 or 3. Alternately, it could be used to increase vehicle velocity for the same cost. Nuclear propulsion is probably essential for any crewed activity beyond Mars. The space nuclear program is an excellent candidate for a multinational research effort because different countries have different capabilities and research interests. NASA would benefit from a coordinated multinational research effort in this area. 7.6 Technology Summary. In order to give future designers a rich and effective set of technologies to draw from, an investment in a broad-based space technology program is prudent. This should be done in a focused but long-term manner, with a clear metric of enabling and reducing the cost of future exploration. There are a number of potential technologies and approaches to be examined, as indicated in Figures 7.6-1 and 7.6-2, which attempt to identify near and longer-term benefits from the investment. Some of these technologies have been discussed above, and others throughout the report. NASA would not be the only beneficiary of these technologies. Other U.S. government and commercial users of space would benefit as well in terms of new capabilities or reduced cost. Consistent with administration planning, the Earth-based benefits to economic recovery, energy technology, biomedical science and health, and protection of our forces and homeland have been indicated. Figure 7.6-1 Technology Opportunities to Impact Near and Midterm Exploration Capabilities and Sustainability. Source: Review of U.S. Human Spaceflight Plans Committee. Capability, Approaches, Benefit to NASA, Other Benefits. Improved LEO launch. Higher volume production of expendables or reusables. Lower cost to LEO. NSS, ComS, Econ, Energy, Protect. Galactic cosmic and solar radiation mitigation. Better risk assessment, mitigation, shielding. Lower mass systems with better human protection. Bio. Autonomous rendezvous and docking. Improved sensors, algorithms, system tests. Enables unpiloted assembly and fueling in orbit. NSS, ComS, Econ, Protect. Cryogenic fuel transfer. Development and testing of fuel management and transfer technology. Enable smaller Earth departure stages or makes planned ones more capable. NSS, ComS, Econ, Protect. In-space restartable engine and boil-off technology. Cycle and engine development of hydrogen or methane engines. Enables longer duration exploration to destinations needing return propulsion. NSS, ComS, Econ, Energy, Protect. Crew autonomy and robotic support. Development of robotics to assist crew in space and on surfaces. Increases efficiency and focus of crew on tasks better done by humans. Bio, Protect. Advanced system design methodologies. Computational, simulation, and decision support systems. Quicker, better documented, and more thorough system designs. NSS, ComS, Econ, Energy, Protect. Advanced materials. High temperature and nano-engineered. Improves durability and strength. lighter weight systems. NSS, ComS, Econ Energy, Bio, Protect. Closed loop life support, mechanical or biological systems, lower mass for human duration. ComS, Econ, Bio, Protect. Methane engine, cycle and engine development of methane engines. Allows better packaged stages that would use Mars ISUR products. NSS, ComS, Econ, Energy, Protect. Aero entry, descent and landing in atmospheres. Development of novel structures for aero braking and entry. Lowers massive systems, enables large masses on Mars. NSS, ComS, Econ, Protect. Technologies are listed in approximate order of decreasing importance and urgency. Other benefits are to national security space, NSS, commercial space, ComS, economic recovery, Econ, energy technology, Energy, biomedical science and health, Bio, and protection, Protect. Figure 7.6-2. Technology opportunities impact longer-term capabilities and sustainability. Source: Review of U.S. Human Spaceflight Plans Committee. Capability, approaches, benefit, other benefits. Surface systems, accessible or inflatable habitats and mobility systems. Lower mass to surface, more capable exploration. ComS, Econ, Protect. Surface power, advanced solar, isotope, or fissile-based. Lower mass to surface, more power for exploration and ISRU. NSS, Econ, Energy, Protect. Lunar in situ resource utilization. Regolith or hydrogen-rich formations derived. Lower consumable delivery to surface. ComS, Econ. Lunar in situ propellant production and export. Reusable lunar to EM L1 tug. Enabling of new Earth, Moon, Mars transportation architectures. ComS, Econ. NEO-based in situ resource utilization. Based on initial sample assays and transportation network. Enabling of new intersolar system transportation architectures. ComS, Econ. Advanced in-space propulsion. Beamed power or nuclear. Smaller in-space propulsion systems, significantly lower mass to LEO. NSS, ComS, Econ, Energy, Protect. Mars in situ propellant production. Atmosphere or ice derived. Lower mass for human duration and enabling of lighter ascent vehicles. ComS, Econ. Earth-Mars cycling spacecraft. Aldrin and multi-synodic cyclers. Enabling new mode of interplanetary travel. Finding on technology development. Technology development for exploration and commercial space. Investment in a well-designed and adequately funded space technology program is critical to enable progress in exploration. Exploration strategies can proceed more readily and economically if the requisite technology has been developed in advance. This investment will also benefit robotic exploration, the U.S. commercial space industry, the academic community, and other U.S. government users. End of Chapter 7. End of Section 17.
Thanks for watching. Please subscribe and click on the bell to turn on notifications.